till when you can hand the observatory over to the science community to actually start doing their astronomy. Okay, and so basically it was a case of getting the telescope aligned, and in particular for us, for the MIRI team, getting our instrument working and making sure that it could perform its science goals. And so yeah, so first off, MIRI, well, the Webb telescope. I kind of assume that for this audience most people know what Webb telescope is about. It's been in the news quite a lot in the past year. So the world's most powerful infrared telescope. I mean, that's kind of specific. People talk about it as though it's the most powerful telescope ever built. It's not really. No, you know, you need to be specific. Conceived in the 1990s, when the Star Trek Next Generation type font was seen as being fashionable, which is why the first logos had that kind of slightly slanty italicized text. Anyway, designed and built in the 2000s, tested and assembled in the 2010s. So this was as the observatory was built up from its sub-elements. At every stage it was tested, mostly at the Goddard Space Flight Center outside Washington, towards the end at the Johnson Space Center in Houston. But finally launched at the end of 2021 on Christmas Day 2021, and flown. Well, it's going well at the moment. Okay, so there are 4 science instruments. So you have the telescope that collects the light, focuses it down onto the instruments. 4 science instruments. 3 of them begin with the letter N, which is short for near, as in near infrared. They operate from wavelengths from 2 to about 5 microns. So, I mean, you know this stuff already, but your eyes are sensitive to light from about half a micron to 0.5 to 0.8 or whatever. So it's 10 times the wavelength of light that your eyes are sensitive to. But the one that I was leading, and in fact that I've worked on for the last 20 years, I mean, I was the instrument scientist before I was commissioning lead. I'm kind of, leading the team that's done all of the testing as well, begins with the letter M, and M is for mid-infrared. So MIRI works from 5 to 28 microns. And as we'll see in passing, that makes it by far the most interesting instrument on the observatory by any objective measure. Okay, so as I said, it was launched on Christmas Day 2021, and it had 6 months allocated to this commissioning phase where we get the whole thing going. And so, the question then is, how did it go? And so, Nature articles, dedicated Scientific Americans, all of that stuff. So in terms of publicity and outreach, it went really, it looks like it went pretty well. In fact, it really did go very well. And so, there have been breakthrough observations being made pretty well every week. There is something that there has been a profound discovery made about some area or another of astronomy. Whether it's dust shells around Wolf-Rayet stars, which you can see in the center nature image there, the fact that the high redshift galaxies appear to be more highly or evolve quicker than was expected, and it's starting to turn up some really interesting results on exoplanets as well. So I have been floating on a cloud of joy since last summer when we finished commissioning and started science operations for Webb. It's just been fantastic, a really brilliant experience. And so I kind of hope I can communicate a bit of that to you. I wanted to load this image quickly. Can you still see this, by the way?
Yep.
You can still see the split image. Okay, this is just making the point about what Webb is. Oh,
we can't
maybe
see
not.
split image, sorry.
No, you can't. Well, forget that then. I'll forget that. Okay, what I was showing, well, I was showing you a Hubble Webb comparison, but it's not essential. Okay, let's just carry on. Yeah, it occurred to me that because it's not actually part of the PowerPoint show, then it might not get shared. Okay, so this is MIRI. This is the last time humans saw the MIRI instrument. This was a picture taken in 2010 or 2009, I think, at the Rutherford Appleton Labs out in Oxfordshire, which is where we did our final testing of the instrument as a subsystem. So what is it? It's an imager and a spectrometer operating at wavelengths from 5 to 28 microns. So an imager, it can take pictures of stars, galaxies, all of that. All of that is kind of finding out or observing the morphology of an object in space. That's kind of interesting. But to actually really understand what you're looking at, you need spectroscopy. You need to look at the colors of the objects, because colors relate to their physical makeup in terms of chemistry, mineralogy, velocity of recession, all of those things that are actually, you know, kind of interesting. So MIRI also has a spectrometer built into it. The key thing here that, you know, the point of this talk really was to make the point that it was UK led. Okay, so it was built by a European consortium, you know, in the good old days. Yeah. So the principal investigators, my boss, Gillian Wright, who's the director up here in Edinburgh at the Royal Observatory at the, well, it's called the UKATC, UK Astronomy Technology Centre. I was the instrument scientist, have been for over 20 years, but the optical engineering lead and the mechanical leads, they were all in Edinburgh. So all of this was led from Scotland, well, from the UK. 10 European countries, 2 US institutes. So that was the University of Arizona and the Jet Propulsion Labs in Pasadena. Mainly academic and government, a very, notably compared to the other instruments, a very young team, and you know, certainly gender quite diverse as well, you know. So it was just, we all hug each other whenever we meet up now. You know, we've just kind of gone through this really life-changing experience that thank goodness has turned out really well. So it's been a very, very positive story. Anyway, delivered this instrument, as you can see here. I mean, it's all metal, all made of aerospace aluminium. The red cover here, these are, you know, in space missions, red items are things that you need to remove before you fly. This is the the dust cover over the lens, so obviously that had to come off, you know. Anyway, yes, delivered in 2012, cooled to 5 Kelvin by its own helium gas closed cycle cooler. So although the observatory Webb is notable because it cools passively by just radiating its heat into the dark blackness of space, we actually had to get even colder than the base temperature that the observatory achieves. Where the telescope gets down to about 40 Kelvin, we need to get down to 5 Kelvin in order that our detectors work. That's the basic reason. Okay, and thereby we can achieve the kind of the quantum limit on sensitivity, which is what we needed to do. Okay, so I've got a couple of videos here I wanted to show you. This first one is of the launch itself, where the main thing for me is the fact that the countdown on here is in French, which I just think sounds so much cooler than, you know, than an American accent. But so hopefully you can hear the sound. And the other satisfying thing about this launch is that I was actually I had to travel. Well, I was going to be in Baltimore at the Mission Operations Center. To the edge of time itself. The edge of time. Begins a voyage back to the birth of the universe. Now I'll turn the sound off. Oh, maybe I won't. Can you still hear me, by the way? Oh, no, that won't work. Never mind. The other satisfying thing I wanted to point out was that after launch, it went pretty well straight into the clouds, which meant that all my colleagues that were actually at the launch center, you know, were couldn't see it, which for me gave me a bit of sort of Schadenfreude pleasure. I was at home in Scotland for the launch itself. Having just arrived home 30 minutes before the launch, so you know I had my own kind of excitement, but mainly at Edinburgh Airport. Anyway, in 2014, NASA will launch a new telescope into space to study the universe as no telescope has before. Okay, so I'm going to, sorry, back to that video. I'm just going to pause it there again, just to make the point that this video was made in about 2008, 2009. It's technically very accurate, but it did refer to the launch as being in 2014. So you know. We suffered many delays during the course of the project, primarily due to finance and American politics, actually, were a big impact. Anyway, I'll play the video a bit further on. Into space to study the universe as no telescope has before. The James Webb Space Telescope will journey 1 million miles away from Earth into the bitter cold of space to search for infrared light, the radiation we humans perceive as heat. Okay, sorry, it won't let me pause where I want it to. Let me just get back out to there. Okay, that'll do. So this is, you know, this is then this image of the observatory. I just want to pause on briefly, and it's really to give you an idea of this idea of passive cooling, which I should say was actually conceived at the observatory in Edinburgh by a guy called Tim Harden back in the 90s. The idea is that in the infrared, we want to have the telescope needs to be very, very cold, because in the infrared, you know, cold is the equivalent of darkness for visible light. Yeah, we don't want to have the telescope emitting its own infrared light, which would then be swamping the light we want to see from distant galaxies and stars. So to get the telescope cold, we deploy this big, shiny 5-layer sun shield and make sure that the observatory is always positioned so that the sun is on the bright, warm side of this sun shield. So the sun is down in this image. You can see the sunlight falling on. So on this side of the sun shield, we've got our warm electronics, the communications with the ground, all of that sort of stuff. On the cold side, the optics themselves for the telescope, all they can see is interstellar space, which is at an effective temperature of about 3 Kelvin. So as long as that reflector works well, then the observatory will try to thermalize somewhere between room temperature, you know, and 3K. And in the event for Webb, it gets down, as I said earlier, to about 40 Kelvin. Okay, so yeah, Tim Harden came up with the idea. We actually did engrave his name on our instrument, and it's not something you're meant to do on space projects, but we did anyway. We put it in a place that was never seen, but it's kind of sandwiched in there. So Tim is out there, at least in spirit, as well. Okay, the spacecraft wasn't launched like this. In order to, it was launched as, it looked a bit like a car that's been through a car crusher, you know, when it was launched. It had to completely unfold. It did that using nearly 300 deployment mechanisms. A lot of them, they were Kevlar strings, actually, that was kind of stretching this sun shield out in its different layers and separating it so its geometry was just right. They all worked, well, they pretty well all worked perfectly. One or two of them were a bit sticky, but it was just a case of upping the current, and they did their job. So that was just an amazing achievement, and I'm not sure anyone was really expecting that to go anything like as smoothly as it did. And this is all, the number up at the top here, this is 1 day after launch to 10 days after launch. So this was, you know, this kind of gave everyone a really good feeling very early on in the project that things were going to work okay. Okay, if there's time at the end, I might come back and you can see the deployment video, but I think we'll kind of crack on. Okay, so as I said, 10 days after launch, the observatory was able to start cooling down because that sun shield was deployed. So it was cooling passively as it was traveling on its way out to the L2 Lagrange point, 1 million miles away from the Earth. That journey took it about 4 weeks. So it was traveling out there during January 2022. So it started cooling down. This plot is then showing you the scale up the side is temperature, along the bottom is days after launch. And you can see here the modeled predictions for how the science instruments would cool down, where the N instruments, the near-infrared instruments, would achieve their operating temperature, which is down here, where they need to be down at about 40K, after day 50 to 60. MIRI, our instrument, remember, we need to get down to 5 Kelvin, so we were only going to get cold and operable after day 100, something like that. So the pressure was on us a bit, because we were the last instrument by some margin to you know, have the chance to actually start taking data and see how well our instrument was working. Anyway, that was the theory. I've actually got the real data here. So you can see, once again, the predictions are the dashed lines here, and then what we were actually measuring are the solid lines. And you can see that things really did go pretty well and pretty smoothly according to model predictions, to the extent that we were actually able to fiddle around with how we cooled the observatory down to optimize some things. In particular, it's the transition through this so-called water band that you can see here at a temperature of around 150K, where there is a danger of ice forming, any residual ice that water vapor that you've taken up with the observatory forming as ice on your optics. Anyway, so that all went really well. Okay, so then we got into the phase for telescope alignment. So this is going through February, March, April last year. And so this was kind of a 3-stage process. The first one was, well, I should say all of these processes worked by looking at a bright star. Okay, there was nothing too much more complicated than that. The first image was that kind of jumbled up blobs and spots near the center of a frame. So the first process was to then tip and tilt each of the 18 primary mirror segments to see which one was associated with which blob, and so then form them into this pattern where we could align I'd say where the wavefront team could align each of the mirror segments separately and then finally bring them together. So this is the kind of the first stage, where just by looking at the size of these blobs, you could get the different mirror segments co-aligned to have a piston difference of down at the level of 1/10 of a millimeter. So it's pretty good, but nowhere near the levels of alignment we actually needed to do our astronomy. So this slide then shows you how this is the thing that was doing kind of the heavy lifting for the alignment in some ways, to get us from that 1/10 of a millimeter precision down to or coplanarity, or whatever you'd call it, down to about 1 micron. And so what's going on here is that each pair of mirror segments then has an optical element which can be driven in front of it. This is all part of the NIRCam, the near-infrared camera instrument. And so each of those little elements that you can see as the rectangles in the image on the top right is giving you half of its light is coming from one mirror segment, half of it from an adjacent mirror segment. By interfering that light and dispersing it in wavelength, which is what the images at the bottom left are showing you, okay, you get a fringe pattern which is analogous to the fringes that you'd see on a thin film of soapy water. Okay, so in this picture of a soap film on the right, you know, stolen from the internet, you can see that where the film is very, very thin at the top, the fringes are wide apart. They get close together as the soap, you know, the soap film is kind of collecting at the bottom of this frame. It gets thicker and thicker and thicker, and so you see narrower fringes as you're packing more wavelengths into the thickness of the soap film. Anyway, so instead of front and back surface of soap film, we're using adjacent primary mirror segments. And so when they are well aligned, you see these broad fringes, which eventually just become a single bright line. So this pair of mirror segments here are well aligned. And then you can see that by having two of these, one that's the blue color and the red color, you can basically stepwise co-align all of the primary mirror segments. And indeed, that's what happened. And that got the primary mirror segment phase errors, as it says in the bottom bullet, down to about a micron, which is less than the one wavelength of our shortest operating wavelength. So that's pretty decently aligned. Okay. There was a final step, though, of fine phasing, and this is where okay, so the technique here is something called phase retrieval. All that you're really doing here is taking very out of focus images by moving the secondary mirror in piston in and out. Okay, so we're just taking very defocused images, as the video is showing on the bottom left. So the forward, you know, you can imagine taking an optical prescription of the telescope and introducing what I'm calling here a wavefront error map, which you can think of as being analogous to a kind of a height map of the mirror surface. So you imagine that you've got a mirror that has bumps and dips in it, or misalignments between adjacent mirror segments. You can feed that into a computer program, and it will predict the images on the left. So if you can solve the inverse problem, which is what phase retrieval does, you can take these images and recover the wavefront error map. And so that's how the ultimate precise alignment was achieved. And so with those wavefront error maps in place, that was done for each of those separate primary mirror segments, where there was some optimization between piston in those mirror segments and piston in the primary mirror, in the secondary mirror, sorry. And you know, we had our optimized images, and they were just restacked, so everything was all of the mirror segments were pointing at the same star, and that's where we were. You know, that's what produced the exquisite image quality that we've seen with the Webb telescope. So that process now can be, you know, this process of unstacking, rephasing, and restacking of when you're pointing at a bright star, that can be run now in a couple of days. So if there's any misalignment event, it can be recovered and corrected very quickly. Okay, stepping back a bit, the theoretical optimum image quality you can achieve requires that you have a wavefront error below a 14th of the minimum wavelength you're observing at. So for us, that would be 140 nanometers at 2 microns wavelength. Okay, that should be, looks a bit odd, that number, but it's so 2 over 14 is 140 nanometers. So that's the root mean square deviation in height, if you like, of the mirror surfaces from their optimum design value. And so what was achieved in the process I've just shown you before the 25th of May was an RMS wavefront error of 55 nanometers, so way below what we needed, much, much better than we needed. However, May the 25th, the observatory was hit by a micrometeorite, and so you can see here is an extracted wavefront error map produced by phase retrieval, and you can see this bright blob at the bottom right. This is where the micrometeor hit and actually melted the surface of the beryllium mirror, caused a little crater which is still there. That briefly raised the wavefront error to 280 nanometers. So briefly, Webb was essentially out of, the image quality was not what we would have wanted. However, but because we've got 18 mirror segments, you can balance that wavefront error across the entire primary mirror surface, and that has brought the wavefront error back down to 67 nanometers. So we're well below the budget, as I say, and you can't tell the difference between the images as delivered and the ideal. Having said that, we don't want any more of these micrometeors to hit. We were kind of unlucky in terms of this one being a bit bright, being quite massive and doing quite a lot of damage. We can't really do with having many more of these events happen. Okay, there are other micrometeors have hit, but they're way down, in terms of their importance. So the mitigation is now in place that if there is a predicted meteor storm going to pass by the Earth and Webb, we turn our back to it. Okay, and that's pretty well it. So telescope alignment was a success. The near-infrared instruments were all working by L+100, which, if you remember, that's when MIRI got cut down to its 5 Kelvin, and we could actually switch on. We had it was L+103 was when we started our commissioning observations, and we had less than 10 weeks to verify that we were able to meet our science goals. And you can read the bullets there that say that give you the details of what we were trying to do there. But that was an awful lot of activity, and I've done this sort of thing on ground-based activities when I was younger, and typically these activities would take, I say here, at least a year. We had to do it in less than 10 weeks. So here are the people that did it. So these are members of the team. That's Misty on the left, Christophe in the middle, Dan on the right. Misty US, Christophe is French. Dan was French. Now he's in Scotland. Anyway, this is our mission control center for Webb. It was on the second floor of the Space Telescope Science Institute in Baltimore. We were staffed 24 hours a day throughout commissioning, as it says, by 12 teams, where MIRI, our commissioning team was one of those 12 teams. So 30 people in this room typically during commissioning. We had a team of 45 people who were there 24 hours a day, with 2 people on console for MIRI at all times. And many people, as it says, supporting events remotely. This is just soak up the colors here. Don't bother about the detail, right? This is a section of our commissioning plan. The colored bars here are named individuals when they need to be present in order to run specific tests, where the tests are these black texts here. So each one of those is an observation, slewing the telescope to look at a star or a galaxy or the Large Magellanic Cloud we looked at a lot. But it was all planned and rehearsed down. We've been planning and rehearsing it for years, basically since 2012, something like that. What we would do in this first 180 days. This is another way of looking at it. The black things here are the black boxes are the tests that we ran. Then the colored lines flow into the colored boxes, which are analysis projects, essentially Python Git-based projects or software, where we'd be analyzing the results coming out of the observations. The colored boxes on the right are then where we, key decision points where we decide, is spectroscopy ready for release for science? So, as I say, planning, and rehearsing. So this is on console. Here's a picture of Polychronis, Greek colleague. And so this is just to give you an idea of the day-to-day work here. He's got his headset on, where you can hear all other subsystems. You can hear the mission operations manager, so you know what's going on. But crucially, you can talk to the people who will actually be sending out our commands in real time to the observatory. There is then the telemetry over here, something like 2,000 MIRI-specific telemetry items that need to be tracked and understood. Green is good, yellow is warning, red is bad news. Okay, the observatory, I should say, was not everything went as smoothly as you might have seen in the press. The observatory went to safe haven state 6 times during commissioning. That's where the spacecraft loses track of where it is. and basically shuts everything down. So you have to kind of reboot from scratch to get things going again. Yeah, you can ask questions about that at the end if you want. And then there are mimics in here, these things that look like these sort of cartoony things. They're ways of visualizing complex subsystems. So our cooler, the attitude control system, you could see, fuel going into the rocket motors, all of that. So it's kind of cool, but, not actually massively useful. Well, it was sort of useful. Anyway, so the science readiness, I mean, this is almost the most important slide, I think, in my whole presentation. So MIRI data analyzed and interpreted within days of being observed by a young, diverse team drawn from across Europe and the US, and diverse in, gender diverse, sure, but diverse in most senses, really. And this is what's really kind of, it's the best experience of my entire career. And I just feel extremely fortunate to have been involved with this team. Amazing enthusiasm and commitment. We took over the library at the Institute because of COVID, really. There's no one else there. But the experience was kind of lifetime unique for everyone involved. Yeah, really good, really amazing experience. And I kind of wish it for everyone in this audience, that you get the chance, stay in this kind of high-tech field, and hopefully you'll get the opportunity to do something similar. Anyway, all of our optical modes were reviewed and declared ready for science, as it says here, between L+174 to L+106. So, in time for the end of commissioning. And, it got down to planning tasks with Post-it notes stuck on the wall. It was amazing. Anyway, what did we see? So we used the Large Magellanic Cloud as a kind of a prime calibration target. The reason for that is that because we have to keep the sun in the same part of the sky relative to the sun shield, you can only kind of rotate the spacecraft about the sun line, okay? The line between the Earth and the sun. But that does mean that you can always look at the north and the south celestial pole. And so the large and the small Magellanic Clouds, these are dwarf galaxies that they're associated with the Milky Way. They are in the south, near the south celestial pole, so we could use those. We could look at them all the time. Anyway, I said we rehearsed and we planned, right? We had simulated images. It's the bottom left image is our simulation. This is a simulation that was predicting not just where the stars would be in their relative brightness, but also how bright they would be. So you can see that there is spectacularly good agreement between what we were predicting and what we actually saw when you compare the left to the right. The things along the left-hand side of this image are our coronagraphs, okay, which I might talk about in a minute. Yeah, I think we'll have time. Okay, so it's the bottom right is the MIRI first light image. The kind of interesting thing that we got when we first saw these images, though, that we hadn't modeled and we hadn't expected, and I can probably see, you can see in this part of the image here, if you can see my cursor, bright star, nothing below it. This one, bright star, blob below it, right? So we had this whole new class of objects we came up with, and it's ABG, and it's short for another bloody galaxy, right? We saw galaxies in every MIRI image, which in hindsight we should really have expected. I think this one here is probably this one up here, right? But it was just astonishing, really, to look in the real universe, and we're looking right through the Magellanic Cloud and seeing field galaxies in the distance, and they're just everywhere. It was kind of sobering. In terms of image, our performance, our image. I'll skip through this quite quickly. Our image quality was indeed perfect. Out at L2, you get hit by cosmic rays. So it's the image on the right here shows the kind of the blast of a whole lot of cosmic rays passing through the instrument, causing secondaries, which then look like photon detections on our detector. But the software clears them up. You can see the image on the left there is showing that the software clears things up pretty well. This one, latent images. You look at a very bright star for half, so we put a bright star right in the middle of our imager field here. And 25 minutes afterwards, you can still see a faint impression of it, but after 40 minutes, it's completely gone, and you're good to go looking at some deep field galaxy. So, the performance of the instrument has been fantastic. Okay, this image hopefully illustrates why MIRI why I call MIRI the most interesting instrument on there. Obviously, no, I'm kind of fond of it. This is an image of the taken by NIRCam of the Cartwheel Galaxy. This was one of the first science data releases back in July last year. All I want to point out in here is that everything in this image is either white or red, okay? White or kind of pinky red or somewhere in between. And that's because the what you're looking at are 3 bands. These are false color images made from 3 spectral bands. And the spectrum is roughly flat between those 3 bands. In other words, it has the same ratio of brightness between the 3 bands, because the spectra of the things you're looking at are pretty well flat. They're either hot young stars or they're red. Red means that, yeah, that's pretty well it. By red, in this case, they emit more at longer wavelengths than at shorter wavelengths. Okay, look at the same Cartwheel galaxy with Miri, and you can see there's far more variety in the colors. And so, although it's a false color image, this time looking at longer wavelengths, you can see that there isn't just a smooth variation of the spectrum between those. Some filters, and it's a different filter in many cases, in the case of each blob, right? Where the blobs here are background galaxies. I should have said that to start with. There's just much more variety. And that's because what you're looking at in these background, the reason for that variety in colors is because you're looking at the mineralogy and the chemistry in the galaxies. So there's just far more information that's given to you by these colors. And they were named Skittles, right, when we first saw them. Again, this was one of those things that was unexpected, but not, we should have realized things would look like this, I guess. But it was just spectacular to actually see it in the first light data. So, I mean, just to illustrate that briefly, as I say, I've made up my own false color image from a bit of that image there. And so it's a bit of the cartwheel at the bottom there. And so these are the 3 colors that I've chosen: 7.7, 10, and 12.8. 10 microns has a strong feature due to silicate dust, okay, which can be seen in emission. And so something that is green, there is a chance, or it's likely, that it has silicate dust as a major component of its interstellar medium. And so this galaxy here, you can see, is kind of greenish, and that's the indication of that there. Okay, so we're running out of time a bit, so I'll move on quickly. Okay, so everything we've been talking about there was the imager. I want to mention the spectrometer, and so the thing about the spectrometer, okay, it measures. Imager, you can measure 2 or 3 colors. With a spectrometer, we could simultaneously measure thousands of colors at the same time as measuring their spatial distribution. So you don't get as many pixels in terms of detail in terms of the galaxy, or in this case a planetary nebula that you're looking at, but you get thousands of different colors, and that allows you to take slices through, image slices at specific wavelengths that correspond to atomic or molecular features. In this case, a planetary nebula. So here, this image is from neutral hydrogen. The one on the right is from ionized neon. And at the bottom, you see the kind of the co-added spectrum that shows that longward of 15 microns, you're seeing dust, the dust component of this planetary nebula. And you get all of this in one shot, in one observation. So you can see it's a very, very powerful technique. Okay, I'll come back to that if there's time. Okay, so that, okay, not necessarily the spatial aspect of that, but the fact that you have those thousands of colors, that becomes important when you're looking at exoplanets. So here are 2 early observations. This is from my PhD student, Niall Whiteford, who's got his PhD last year. These are 2 early observations of 2 exoplanets that look completely different, okay, which is kind of interesting. The one at the top right, this WISE 1828, you can see the complexity in the spectrum there is due to the fact that you're looking at molecular bands and molecular lines in the atmosphere of this exoplanet. So primarily the feature in brown at between 10 and 11 microns, the kind of the double dip there, that's due to ammonia. This spectrum is quite similar to the spectrum that you'd see if you looked at Jupiter. The difference is that this is not, Jupiter's like a light hour away from us. This exoplanet is 35 light years away. So Webb really is opening up, in terms of sensitivity, our ability to look at exoplanets within 100 parsecs or so of the Earth. The one at the bottom is kind of interesting because it has none of these features, right? It's a lot smoother. Apart from maybe around 9-ish microns, you might see this little dip here. That's actually due to the silicate dust I was talking about in terms of the galaxy earlier. Okay, so what you're seeing here, I've kind of given it away. You don't see the molecular lines in VHS 1256 because it's blanketed with clouds. Okay, and so again, you look at the real world or the real sky, and you start to see an awful lot of variety And you know, it's exciting. Yeah, it's exciting because those are kind of the first two exoplanets we looked at, and the spectra are very, very different from each other. Anyway, moving on. Okay, we have other tools for studying exoplanets. So here, this is our low-resolution spectrometer. This is measuring the spectral, you know, the colors, the spectrum of a planet as it passes in front of its parent star. So you see this dip in the light from the star because the planet's going in front of it. If you disperse the light and do some differencing of you know, before and after you go through this dip, you can measure the planetary spectrum. We were expecting to be able to measure down to 100 parts per million in terms of the, you know, the spectrum we could see as a fraction of the brightness of its parent star. We've actually managed to achieve a factor of 2 better than that. So that opens up, you know, the exciting possibilities of being able to detect things like traces of an exo, you know, biology in another planet. So this example is from a theory paper that was saying, what if TRAPPIST-1c? TRAPPIST is an exoplanet. What if it was Earth-like? Well, you might expect to see ozone. Ozone would be an indicator of oxygen in the planet's atmosphere, which in turn might be an indicator of you know, photosynthesis and life going on that planet. In the event, it looks like TRAPPIST-1c is a blasted rocky ball, but never mind. Okay, I want to finish really by getting back to the team and what the team achieved, and it's a little vignette, as I say here, which is the coronography. Okay, coronography is it relates to exoplanet detections. The idea here is to have a dot in the focal plane that you can hide a star behind. By blanking out the light from the star, that gives you the opportunity to see light from a planet that might be orbiting that star. Okay, so we have a conventional, you know, the simplistic dot that we do have in MIRI that's in the focal plane. These other 3 channels here, these other 3 regions, they're also coronagraphs, but here you need to get the star behind that cross. Okay, this cross. Okay, the point I'm getting at is that we needed to position it to an accuracy of a 20th of a pixel behind that cross, and that is really not an easy thing to do. So on the ground, okay, we would do that by flood illuminating the coronagraphs with extended illumination, and you would see that black cross, and you'd be able to, you know, locate using geometry and just line fitting where the null was, and that worked fine. This is our flight image on the right-hand side, and you see the vertical dark line. I mean, it does look a bit, you know, bit crappy all round, but you see the vertical dark line, but instead of a horizontal dark line, we see a bright line. Now, this was a stray light feature that we weren't expecting, that comes from the observatory, but it completely broke our methodology for aligning the coronagraphs. And so in only a few days, and I mean, this was like 4 days, we had to devise, implement, and execute a new methodology for finding the nulls. And so that was achieved primarily by our colleagues our coronagraph experts in Paris, who came up with this by doing shift work where, I mean, one guy, you know, this is Pierre Baldoz, he would sleep, wake up to pick up from analysis that Anthony Boccoletti had been doing, carry on with it. He'd get sleep, Anthony would take over again. You know, it was just a crazy few days, but it worked. The methodology that was come up with was to do this kind of small dither pattern where you know that you're close to the position of the null, and then by interpreting these complicated speckle patterns, it was possible to infer where the real null was. That all got tested and was got working, as I say, in about a week, but without impacting the plan too much. Okay, but it was great. It was a great experience in hindsight. Very, very stressful, but you know, stressful in a kind of good way at the time. And again, the team did amazingly well. Anyway, we identified where that's those things. We called them glow sticks in the end, the stray light features, and they were coming from a warm region at the bottom here. This is outside the science beam. You know, there's the primary mirror. They were coming from a warm region under the primary mirror, where the light was then reflecting off the secondary mirror, then scattering off this strut, and scattering again, in fact, of some optics in here, and that's how it was then getting on to illuminate those glassy elements in the focal plane. So it's kind of a big deal. Anyway, this is the end result, is that we got the whole thing, got the coronagraphs working, and so these are images of an exoplanet Now, this is a direct image of an exoplanet taken with the coronagraph, where the star, the graphical star symbol is marking where the parent star is. And you can see that we've got the alignment so good that the star has been completely removed in these images, nulled out, and you can see the exoplanet here. The reason these particular images are maybe of some interest is that this particular filter at 15.5 microns, this is sensitive to carbon dioxide. So if you see a dip here, that's showing you that there may be a lot of carbon dioxide in the target planet you're looking at. And that, again, is another indicator of a terrestrial type planet. You see CO2 in both the Earth's atmosphere, but also in Mars and Venus. So it's not a unique identifier, but it is certainly an interesting indicator. And I think that's it. So, as I say, MIRI, JWST as a whole, a spectacular success. Built, tested, and commissioned by a joyous team. I mean, it really, an amazing team, drawn from European and US institutes, but all led from Edinburgh, right? So from the UK. And so, when I talk to people about the project, especially groups like this, it is a reminder that, you can get involved in this sort of thing, and it can give you the most satisfying experience you could expect to have from work, I think. It's great. And anyway, and the direct comparison, Spitzer was the best previous observatory. And you can see the gain that we get in the mid-infrared in terms of detail that you can see, but also sensitivity. It kind of it has been that orders of magnitude improvement that you need to really make a breakthrough in astronomy. And then finally, and there's the team again. There's Christoph again, and Danny, and Vincent, and the rest, with making a joke about our glow stick stray light feature at a party. And so I think that is it. So I will just put these down, and then shall I stop sharing for a minute? But I can. By the way, has anyone heard a word I've said?
Yes, we have.
Well, that's good to know. Thanks. I don't know how to stop sharing. I'm assuming there might be questions. But yeah.
You've managed to stop sharing, so it's all right.
I have. Okay.
We were going to go on to the next speaker because we don't have time for questions, but she has told us that her internet has just briefly cut out. So we actually do have time for questions.
Brilliant.
So we have one from Jost, I think.
Jost, yeah. Hi. Hello. Hello again. Yeah.
So you said during the talk that you spent something like 10 years preparing for and practicing this 10-week commissioning phase for MIRI.
Yes.
And I was wondering, I guess the original plan, without delays, was for a much shorter practice period. So how did those additional years help you? Or was it just getting sick and tired of it?
That is an entirely fair question, I think. Well, you make a good point. Yeah, I mean, we would not have been ready. Absolutely would not have been ready in the same way. We were very fortunate during commissioning. Okay, it turned out we had the plan was in place. It would have been an awful lot more. Okay, the way it would have worked, well, you could have just gone up and started observing. Okay, with a much shorter plan. In hindsight, we may well have got away with it with only like 2 or 3 people out of the 40 people in the team having nervous breakdowns. As it is, we all got through without nervous breakdowns because of the planning. Yeah. Put another way, we had that problem with the stray light with the coronagraphs that was fixed. Yeah, in real time. If we'd had, let's say, 2 or 3 other problems of a similar magnitude, that would really have we would have tipped into being in a really bad way very quickly, primarily because because we were the last subsystem to get commissioned. There was an awful lot of kind of not just press, but the other teams were wonderful, right? But there was a lot of focus on everything else is working. What can possibly go wrong with MIRI? So a lot of people it would have, the stress would not have helped if we hadn't been as well prepared as we were. But you're quite right. Yeah. Okay, that launch date of 2014, I think that video was made like 6 years before launch, and we did actually have the plan. It was kind of started being in place around 2010, 2011. We had tested our instrument as well, so we kind of knew we'd characterized it in the lab, but knowing which star to point at and having the simulations in place and having the code in place that got us to, to do all of that, that didn't exist. And so, yeah, it would have been a lot more, it would have been much more stressful, and the science data products that the users would have have been getting since August would have been much lower quality. Yeah. All of that training and practice meant that the pipeline, the analysis pipeline that actually produces like the publication quality data, that was in really good shape, especially for MIRI, for our instrument. But it's a good point. It's a good point. It would have been tougher, right, and worse if we hadn't had that time, if the launch had been on time. And we used every minute of the delays usefully. Yeah. But it's a great question. Yeah. That's to say. I won't say a good question, but a very fair question. You know what I mean? I mean, it is a good question, yeah. Sorry,
Thank you so much.
No, it's fine. Any others? Or do you want to move on?
Looks like Isha from KCL Space has a question.
Yeah. Hi, Isha.
Yeah, hi Alistair, lovely to meet you. It was an amazing talk as well, learnt loads from that, and I'm really excited to see that the UK space industry is very forthright and they're doing a lot of things. And especially with JWST, it's like amazing the achievement that lots of space people around the world have managed to do with this. So my question is generally, how would micrometeorites affect the lifetime of JWST? And do you ever think we will be able to see a habitable exoplanet through JWST?
Oh, okay. Well, second question. Yes, definitely for habitable, but it's habitable. That definition is changing, right?
Yeah.
So habitable, is it in the habitable zone? Well, maybe, but if it's in the habitable zone of a star that has high energetic outflows every year, you really wouldn't want to live there. Okay. Yeah. So, but actually, being able to detect signs of life, like a biosphere. That has never been was never an objective of Webb. It is capable of doing it, but it's not designed to do it. So we kind of have to get lucky with the target. Yeah. If there's an exo-Jupiter that happens to have, like, I don't know, giant plankton creatures swimming around its atmosphere that are producing oxygen, sure, there's a chance we can detect it. All I'd say is that, and no one really knew, I don't think anyone really knows what the probability was of getting lucky and observing something that has signs of life. But whatever that probability was, we're about a factor of 2 better because the spacecraft is working so well. Okay, yeah, I think there's a chance, right? But it's it is just odds. I don't gamble. I don't bet on anything.
Yeah, no, it's just generally. Yeah.
So, but there is a chance, yeah, and not habitable, but actually a sign of habitation, which I think, we've detected lots of habitable planets already, yeah, with Kepler and other missions. I'm sorry, Isha, what was the other question?
The first question is about micrometeorites and how that affects JWST
sure.
lifetime. Yeah.
Yeah, well, as I said, okay, hopefully it was clear. We got hit by a micrometeor in May. That did damage. That did permanent damage to the primary mirror, but not enough to actually impact the image quality. If we got another, I don't know, but if we got another 5 or 6 of those, you'd start to see an impact. We just couldn't compensate for it by, unstacking, realigning, and optimizing again. And so we don't want to get hit by any more. That one was a bit of a fluke. It was out in the bell curve for size. But this mitigation then of essentially, the meteors come from in front because you're orbiting around the sun. And so when there's a meteor shower due, then we turn and look back back where we've come from in the orbit. That's the mitigation. But that is not going to be perfect. We'd have to get more unlucky, but it could still happen. The limit on the mission lifetime is actually the amount of hydrogen fuel we've got. So it's rocket fuel, and so that's why the launch by Arianespace was so fantastic, because it's the same fuel, the same liquid fuel, which we use for station keeping at L2. This is going backwards, right? L2, it's a metastable Lagrange point, so you have to have a little orbit, or a little burn every few weeks to keep you on at L2. And so when that fuel runs out, we'll just drift away from L2 and things will start going wrong, hopefully quite gracefully. The mission was planned to last for 5 years with a 10-year goal. Looks now like it's going to be more like 25 years, but that's based on the fuel. So to step back, the reason the launch was so important was because the injection to get out to L2 used the same fuel that we now use for station keeping. So Arianespace did it super efficiently, and it means we've got the maximum volume of fuel left.
Oh, I see. So
yeah.
So basically, when JWST dies, essentially, like in the future, it would just drift away from LT2 forever and not just go out into interstellar space. Or just
it'll stay in orbit around Earth, I think, unless it gets a really big perturbation, maybe in a few million years' time. I imagine it'll get dragged back. I'm kind of positive about the future of humanity. I imagine it'll get dragged down and put in the museum. I hope so.
Yeah, that's true. The British will definitely try to recapture and put it in a museum.
The British,
yeah,
may not belong to them, but yeah, who knows?
That's never stopped the British.
It never stopped the first time, so I doubt it'll stop them now.
I think my Belgian colleagues may have a claim as well. But anyway, yeah. What was I going to say? Look, there are all sorts of stories about this. Yeah, I mean, I'm sorry, I skipped over a couple of slides for time.
No, it's all right. It's okay.
But, one of them that's kind of I've just had such an amazing year, and the team have as well. But the for the mid-orbit correction, there was again, and it was working with NASA. There's some amazing people involved in this project. The planning included having. Oh, can you still hear? I seem to have frozen. Can you still hear me?
We can still hear you. Yeah.
Okay, great. Yeah, my sound's good. Yeah, there was so for the mid-orbit correction, there was one that was I think it was run after about 2 days after injection to L2. There was a planned orbital correction, and there was actually two corrections were planned in case the first one that was run from Baltimore from the Mission Operations Center that went wrong. There's a whole other kind of shadow operations center set up at Goddard, which had a burn planned for 2 days after, or 2 hours after the planned burn. Yeah. So in case the planned one went wrong, the idea was that they could then have one ready to go. Yeah. So that we wouldn't. Yeah. It was just. It was really, an awful lot of planning. Yeah. As Jost would say, if the orbit gets delayed, you don't just sit there waiting, and twiddling your thumbs. You do actually really dig down into the details of what could possibly go wrong and mitigate it. And the end result for Webb, and I hope the other point that you'll get is, okay, there were a couple of hundred people in total, and we had 45 people in our team doing the commissioning, but really we were just, the reason it went so well is because of the high quality and professionalism of all of the manufacturers, all of the people who'd worked on the project for a couple of years back in 2005. It seems that everyone had just been so enthused by the project. They'd all just done a fantastic job, and so everything pretty well, nearly everything went perfectly. So that's why, it really gave me just a really good feeling about people that work in our field,
Oh yeah, definitely. I really find that people in the space industry are very much, they work together a lot more, and it's more like sense of community and collaboration. So I think that's going to be a main feature of the future of space, and that's why it's very exciting to go into the space industry at the moment. Collaboration, and people just really want to help each other. And I see the JWST, look how amazing it happened. It's a great moment for everyone.
Yeah, exactly. And everyone that's had a bit of it. I mean, we did our testing at RAL, as I say, in Oxfordshire, but it's labs around Europe, and it was mainly academic, groups that worked on it, and the amount of of affirmation for the team that's come out of it, and for so many people, it's well worth every penny of the $10 billion. It's a third of a track and trace scheme, right? That's cheap. Right? So yeah. Okay, Isha, I think that was it. Yeah.
Yeah, that was it. Thank you.
Brilliant.
So we seem to have Amy seems to have be having a few internet issues. So instead of being her next, we'll be starting with Jost. So I'm gonna hand it over to Holly to introduce them.
Okay, I'm gonna duck out. So.
Okay.
Bye, Alistair.
Yeah, look, thanks very much, everyone. It's been lovely.
Thank you very much for your presentation.
No, it's a pleasure. Thanks a lot. Bye, everyone. Bye.
Bye. See you. Have a good day.
So I'm just going to share that tab.
So our next speaker is Dr. Jost Wiegender. They are a postdoctoral research associate at the Experimental Particle and Astroparticle Group at King's College. Today they'll be giving a talk on supernova neutrinos in the multi-messenger era. So Jost, I'll hand over to you.
Okay, thank you. So let me share my screen. And there we go. Can you see my slides?
We can, yeah.
Yeah.
Excellent, excellent. So thank you very much for organizing this cluster event and for inviting me to talk. And yeah, I'm going to be talking about supernova neutrinos in the multi-messenger era. And I think you're probably mostly familiar with electromagnetic astronomy across various wavelengths. But I'm going to be talking about neutrino astronomy today, which is a little bit different. And I realize many of you may not have a background in particle physics. So I'm going to start by giving kind of an introduction to neutrinos. What are they? Why did we even think they exist? They might exist. But before that, a few words about myself. I'm originally from Germany, grew up near Berlin, and then studied in Munich, nuclear particle and astrophysics, and came to the UK in 2015, before the Brexit referendum and all that stuff, to do my PhD at the University of Sheffield. And then I finished that in late 2019 and joined King's in April 2020, which is a great time to start a new job, of course. So I work on this experiment called Hyperkamikande, which is a neutrino detector that's currently under construction in Japan. And my main research question there is, how do supernovae explode? And I also work on something called SNOOS 2.0, which is a collaboration of neutrino detectors that I'll talk more about towards the end of this talk. So to start with, I want to go back 90-something years to the 1930s. And back then, nuclear physics was starting to pick up steam. And physicists had discovered beta decay, where this nucleus emits an electron and turns into a different nucleus. And nowadays, the way we describe this is a neutron in the nucleus decaying into a proton and an electron, right? And so physicists in the 1920s started investigating this process, measuring, for example, the energy of the outgoing electron. And if you look at this as a physicist, you see, oh, that looks like a two-body decay, right? So one initial nucleus decaying into another nucleus and an electron. And if we know the masses of all of these particles from conservation of energy and momentum, we should be able to figure out what exactly is the energy of that electron. So you do the calculation, and you would get one specific energy. But then when you measure the energy of that electron, you find that it's actually a bit lower than that. And it varies quite a lot. It's not one fixed energy as you'd expect. So this is weird, right? This seems to violate conservation of energy. And that really puzzled physicists for several years. And some were willing to give up conservation of energy on subatomic scales. But this guy here, Wolfgang Pauli, had another idea, and he wrote in a letter to some colleagues addressed to "Dear radioactive ladies and gentlemen," he wrote that he resorted to a desperate way out to save conservation of energy. And Pauli's suggestion was that there's a third particle produced in this decay that we just didn't see, but that transports away the missing energy. Now, Pauli originally called this particle neutron because it was neutral. But of course, 2 years later, James Chadwick discovered what we nowadays call the neutron. So Pauli's particle was renamed neutrino, which is basically botched Italian for little neutron. And this name was popularized by Enrico Fermi when he published the first theoretical description of beta decay in, I think, 1934. Now, you may wonder, okay, but why didn't we see this neutron or neutrino? And the reason, in a nutshell, is that neutrinos are kind of like ghosts. You know, they can quite literally go through walls or through your body. In fact, you've got billions of neutrinos going through every square centimeter of your body right now as you're listening to me. And so, of course, physicists looked at that, and the first people to estimate how likely neutrinos are to interact with other matter were Bethe and Peierls in 1934. And they concluded in their paper that there is, quote, no practically possible way of observing the neutrino, which is a sobering conclusion. So we were very sad, but we just gave up. End of story. No, of course not. So, you know, it took us over 20 years after that to actually detect them. But I'll talk about that in the next section. First, I want to talk about something else. Go off on a bit of a tangent here. I talked about 4 people thus far. Wolfgang Pauli, who came up with the idea of neutrinos. Enrico Fermi, who published the first theoretical description and popularized the name neutrino. And then Hans Bethe and Rudolf Peierls, who were the first to estimate the interaction cross-section of neutrinos. And what they all have in common, in addition to all being white men, because physics back then had even worse of a diversity problem than it has now, what they have all in common is they all became refugees in the 1930s, right? They fled from fascism in Germany or in Italy to the UK or the US. And those are not just a few isolated cases. That affected a lot of other physicists as well. For example, Lise Meitner, who's a brilliant theoretical physicist who described the theory behind radioactive decay experiments, or Emmy Noether, who is an amazing mathematician, maybe one of the best of the 20th century, who described the mathematical foundations of conservation of energy or momentum, for example, and many others. And these are not just, you know, historical cases. We're seeing these effects even to this day. Like just a few years ago, when the Nobel Prize was given to these 3 people for the discovery of gravitational waves. You can see one of them, Ray Weiss, was originally born in Germany. And he fled with his parents to the US when he was a little child. So we're still seeing the echoes of this today. Now, in total, about a quarter of all physicists were dismissed or driven from their positions in the 1930s by the Nazis. The number of foreign visitors dropped very quickly, and a lot of these physicists moved/fled to the US. And that helped accelerate the shift towards English becoming the kind of lingua franca of physics. And it turned the US into the center of the worldwide physics community, which is a position it's still holding today. And of course, over the following years, during the Second World War, many of these immigrant physicists, including Fermi, including Bethe, contributed to the Manhattan Project and built the first atomic bomb. And I always like to refer to this talk here by Dr. Chanda Prescott Weinstein for a more detailed history of physics in Nazi Germany, and which is quite a fascinating tale. Now, I think you could give a whole multiple hour-long talk about the Second World War, about the Manhattan Project, which I don't have time to do now. So I'm going to skip over that and going to return in the 1950s and look at the aftermath of that. Because after the Second World War, Los Alamos, where the Manhattan Project had taken place, turned into a national laboratory, doing a bunch of research in different areas, even to this day, including work on developing and testing atomic bombs. And so that was what this group here of Frederick Rines and Clyde Cohen was working on. And I think if your day job is to build and test nuclear weapons, that really puts you in a weird state of mind after a while, right? Or as Frederick Rines described later, quote, "Bomb testing was an exercise in thinking big. Whenever we thought about new projects, the idea was to set the most interesting and fundamental goal without initial concern as to feasibility or practical uses." And now one of these interesting and fundamental goals without, that may not be feasible, may not have obvious practical uses. One of these goals was detecting a neutrino. So they thought about how to do this, how to detect neutrinos using the tools available to them, which, weirdly enough, included nuclear weapons. So here's the first idea they came up with, and they called this Project Poltergeist. Right. The idea is you dig a hole in the ground for your detector. Then you place a nuclear explosive here nearby, and you trigger it. Boom. And then after the explosion, you wait a while for the shockwave to subside, for the radioactivity to die down, and then you dig up your detector, see if you found any neutrinos. So that's their idea. They went to their boss and had what must have been a fascinating conversation. Basically, hey, can we have a nuclear weapon to do some particle physics? And their boss said, yeah, sure, that sounds good. As Rines later said, life was much simpler in those days. So they started working on this proposal in more detail, started designing a detector. And then after, when they were working on, they presented this idea to the larger group at the laboratory. And someone there had a pretty clever idea for how you could use, instead of a nuclear explosive, how you could use a nuclear reactor, like a nuclear power plant, to do the same experiment. So you wouldn't have the same kind of brief, intense burst of neutrinos, but you would have a long-term, steady flow of neutrinos. So if you can reduce your backgrounds enough, that would make it a lot easier. So this experiment, as shown here, was never actually performed. But instead, they went to a nuclear reactor, did this experiment first in 1953, found a bit of evidence, but it was not quite conclusive, and then redid it with an improved detector at a larger nuclear reactor a few years later, and finally discovered neutrinos, and earned the Physics Nobel Prize for that. Now, in the decades since, neutrino physics has grown dramatically as a field. So you can see on the top right here, this is the number of attendees at the largest conference in the field. You can see over the past 50 years that has grown dramatically. And I would argue that neutrino physics is today the most exciting area of particle physics, because it's very versatile. Right? You get neutrinos from human-made sources like nuclear reactors or particle accelerators. You get them from cosmic rays, from outer space, impacting the atmosphere and producing atmospheric neutrinos. You get them from our sun, from supernovae, which I'll talk more about in a bit, and from many other sources. And so neutrino physics cannot just tell us about properties of these neutrinos, but it can also answer questions in astrophysics. For example, why does the sun shine? And it's actually our old friend we saw a couple slides ago, Hans Bethe, who actually came up with the detailed processes of how nuclear fusion produces energy in the sun. And you can see there's a bunch of different reactions here, and several of them produce neutrinos as a side product. And so these neutrinos are so kind of ghost-like that they can actually escape from the center of the sun. They can travel to Earth. And so if we detect them on Earth, we can learn about nuclear fusion in the sun. And we can measure, for example, the temperature at the core of the sun, which is 15.5 million kelvins plus or minus 1% uncertainty. So we know the temperature inside the sun about as well as the temperature outside our own front door, which I think is a pretty amazing achievement. But now let's move to today, and let's look at how we use neutrinos to study supernovae. And supernovae are these exploding stars. Like here, this is a famous one called supernova 1987A, which happened in the Large Magellanic Cloud, basically our next door neighbor on a galactic scale. And this was the only time we ever saw neutrinos from a supernova thus far. Now, for supernovae, there's this simple rule of thumb, which says, no matter how big you think supernovae are, you're wrong. They're much bigger than that. Right? Supernovae are these giant explosions where this one single star, as shown in the picture here, will shine about as bright as a whole galaxy of billions of stars. Right? And the visible light from that explosion is just a tiny fraction of 1% of the total energy output. Right? Most of the energy is emitted in the form of neutrinos. Now, supernovae also form remnants like neutron stars or black holes, and the outgoing shockwave can enrich the nearby environment with heavier elements and collapse gas clouds to form new stars. And by enriching the surroundings with these heavy elements formed in the supernova, they make life possible, right? So all in this periodic table of the elements, everything in green is produced by supernovae. So that's things like the oxygen in your lungs, or the calcium in your bones, or the silicon in the computer chips you're using to listen to this talk right now, right? So life as we know it simply could not exist without supernovae. And yet, we don't quite know how they explode. And that's the same problem as with the sun earlier. With electromagnetic telescopes, we can only ever observe the surface of the star or the supernova. But to see what's going on inside the star, as whether during its lifetime with nuclear fusion or as it explodes in the supernova, we need some other way to look inside there. And neutrinos are one way to do that. So the one I'm working on is currently under construction in Japan, but it's part of a larger family of neutrino detectors. So the first one was called Kamiokande, and was built back in the 1980s. It's named after the nearby town of Kamioka. And Kamiokande contained about 3 kilotons of water, and it detected neutrinos from this supernova 1987A I talked about earlier. So this was basically the birth of neutrino astronomy, and the leader of the experiment, Koshiba Sensei, received a Nobel Prize for this discovery. But after a while, we were hitting the limits of what we could do with a detector like Kamiokande. So we built a bigger one, creatively called Super Kamiokande, and that started in 1996 and is still running today after almost 27 years. And Super Kamiokande detected evidence for neutrino oscillations, where different types of neutrinos change into each other back and forth as they travel, which also showed us that neutrinos must have mass. And this earned Kajita-san the 2015 Nobel Prize. But today, we're again coming close to the limit of what you could do with a detector like Super K. So we're building an even bigger one, very creatively called Hyper Kamiokande. Details of the Nobel Prize still to be determined, of course. Now, Hyper Kamiokande is built in Japan, deep inside the mountain, about 650 meters underground. And this is so that it's shielded against all the cosmic rays impacting the atmosphere. So all of those particles basically get stuck in the mountain overhead, and only neutrinos, which are kind of ghost-like, can make it through and enter our detector. Now, Hyper Kamiokande is an absolutely huge underground cavern. You can see 71 meters high, 68 meters in diameter. So to give you a sense of scale, you could fit most of Tower Bridge. If you cut off half the tower on the side there, because who needs that half tower? But you could fit most of Tower Bridge inside this detector. Right. So that's an absolutely huge one of the biggest human-built underground caverns. And inside, and this is a photo from taken inside Super Kamiokande, you can see it's this giant space that's filled with ultra pure water. And you can see here there's a human on a boat for scale. Now, in this water, most neutrinos will go straight through without leaving a trace. But every once in a while, we're lucky. One of them will interact with the water and will create a tiny flash of light. And you can see all over the inside walls these kind of golden circles. These are photosensors, which detect this burst of light. And that's called Cherenkov light. That's actually the same as if you see pictures of nuclear reactors, where you can see this kind of bluish glow in the water. That's the same physical effect. And these photosensors, there's one next to me for scale. So you can see they're quite large, about 50 centimeters in diameter, and extremely sensitive and can pick up even a single photon. Right. So we're building this huge detector, and that's not just us here at King's. That's a huge group of over 500 scientists from about 20 countries working together. Right. Technically, right now 19 countries, because Russia is a bit of an issue. But overall, this is an amazing example, I think, of international collaboration, right? You've got people all over the world working on different aspects of the detector and building this huge experiment. And it's absolutely amazing to have collaborators in Japan, in Korea, in Germany, France, Italy, Canada, the US, Mexico, and so on. But there are also some difficulties associated with that. First, and probably biggest one, is just that you span a whole lot of different time zones. So it's a bit tricky to find a meeting time that works for everyone, right? So I've had meetings at 6 a.m. or I've had meetings that run past midnight, simply because of these time zone issues. Yeah, but then another thing that took me a while to notice is that in these different countries, there are often quite different social norms. There are different, for example, laws on LGBT plus rights and so on. And for me, as a queer person, that can be a bit tricky if I go to a meeting in one of these countries, or to a conference. I'm not always certain like what the level of social acceptance is, whether I can, for example, talk freely about my partner, whether I can include my pronouns, they, them, on my slides, stuff like that. So that can be a bit tricky. Okay, enough about hyperchemical. Let's talk about how we plan to use it to study supernovae. And what I want to emphasize here is that supernovae are really fundamentally a multi-messenger event. Right? You produce neutrinos, shown here in red and pink, and this is the luminosity over time after the start of the supernova. So you can produce these neutrinos almost immediately and with a very high luminosity. But you also produce gravitational waves, and then a couple of hours later, because these neutrinos are escaping at almost the speed of light, immediately as the explosion happens. But the light is only produced when the shock wave, which moves slower than the speed of light, when that shock wave breaks through the outer layers of the star. That's this shock breakout burst here, right at the start. So this light is emitted a few hours after the neutrinos. And now these different messengers can transport away different information. For example, neutrinos tell us about the nuclear reactions going on inside the core of the star as it explodes, and can tell us about the explosion mechanism. Whereas gravitational waves tell us mostly about the very compact, what we call a protoneutron star at the center of the supernova. And finally, the electromagnetic light tells us about mostly the outer layers, what they are composed of, and about the nucleosynthesis that takes place there, forming different heavier elements. Now, because these neutrinos and gravitational waves are produced hours before the light, we can actually use them to build what we call a supernova early warning system, or SNOOS, so that when we see these neutrinos, we can tell the world's astronomers, hey, there's a supernova coming, get your telescopes ready. And this idea was first discussed in the 90s, and this network, SNOOS, started over 20 years ago now and has been running in automated mode since 2005. You can see right now it spans 7 detectors across the whole globe. But in the last couple of years, mostly during the pandemic, we've started to develop what we call SNOOS 2.0. And the basic question there is, what would SNOOS look like if we were to build it from scratch today, knowing what we know about multi-messenger observations, all the stuff we didn't know back in the 90s. And you can see there's a photo here from a collaboration meeting last summer. And so SNOOS 2.0 will feature quicker alerts. It will reach a bit further, and we will try to get at least a rough sense of where the supernova is located, basically by triangulating with all these different detectors. right? Because if the neutrinos arrive at, for example, these detectors in Japan first, and then maybe 5 milliseconds later they arrive in Europe, and then another 5 milliseconds later they arrive in the US or Canada, then we can tell, well, the neutrinos probably came from over there on the right side of the screen. So a supernova is probably somewhere there in the sky, right? It's not very precise, but it can tell us at least which telescopes around the globe are probably able to see it, and what area of the sky should we target. And we're also developing follow-up strategies with both professional and amateur astronomers. And if you want to sign up and get an email alert when we detect this neutrinos from a supernova, you can go to snooze2.org and sign up to the mailing list there. Don't worry, it's very low traffic. Okay, so I think I'm at the end of my time. So I'll summarize. We talked about the 1930s, about where does this idea of neutrinos come from, and we talked about how ghost-like they are. We then talked about the first detection of neutrinos and about solar neutrinos, how they let us study nuclear fusion inside the sun. And then we talked about supernova neutrinos and this supernova early warning system we're building right now. And in parallel, we talked about how at each of these stages of the history of neutrino physics, there are some links between physics and politics, right? With refugees in the 1930s, with Los Alamos and the Manhattan Project in the 1950s, and today with this international collaboration. So what I want to leave you with is this idea that you cannot separate physics from politics. You never could. And even today with Brexit, with actually UCU strikes right now because of working conditions and pension cuts, you cannot separate physics from politics, because science sometimes happens in a physical vacuum, but never in a historical one, never in a societal one. So with that, thank you for your attention, and I look forward to your questions.
Thank you very much, Jost. I think I've got time for one question, so if you have one, please raise your hand. Alan, do you want to go ahead?
Yeah, I did. So I know that we're currently with SuperK at the moment, and SuperK allowed us to discover the oscillations of neutrinos between the different flavors. So what do you think we're going to be discovering with HyperK? Any ideas?
So there's a couple things. First of all, one of the reasons we're building HyperK is I thought I said kind of in passing, we're hitting the limits of what we can do with a detector like Super Kamiokande. And that applies to these neutrino oscillation measurements as well. So right now there's this one really important physics parameter called delta CP that we haven't really measured yet, where we technically have a measurement, but the uncertainty is so large it could be pretty much anything. And this parameter is really important because what it tells us basically is whether and by how much neutrinos and antineutrinos oscillate differently. And that's a really important question because if neutrinos and antineutrinos behave differently, that could be responsible for why we have this universe today that's dominated by matter with very little antimatter left. So if we're seeing a few hints that this parameter has a value where neutrinos and antineutrinos are different. So if this is confirmed by Hyperkamiokande, well, we will be able to measure it quite precisely. Then this might tell us that neutrinos are why we have anything in the universe at all, right? And why matter and antimatter didn't just annihilate, leaving an empty universe. So that's one thing, and probably the most important thing. Then we're going to be doing precision measurements of all the neutrino oscillation parameters that we mostly already know, to become more accurate in our predictions. We are going to look for solar neutrinos, trying to understand the sun better, because there are still some discrepancies there between what our observations in neutrinos tell us about basically the composition of the sun in terms of heavier chemical elements, and what the standard solar model tells us. Then we're going to look for neutrinos from supernovae, of course. And we are also going to look at proton decay, right? Because we have this huge tank of water, which has a lot of hydrogen atoms, so basically free protons. And if some of them decay, that could tell us about a grand unified theory of physics at much higher energy scales, where our current accelerators don't reach, like the LHC. So there's a lot of different areas that we're going to look at, and then of course there's always the unknown unknowns. There's always a chance that if we go there and look, we might see something we never expected. So I hope that answers your question.
Sorry, I didn't realize my mic was off. But thank you very much for answering my question, and also thank you very much for your talk. It was really informative, and it's actually my area of my third year project, so I know who to come. I know who to come to for questions.
Nice.
Thank you very much. So our next speaker today is going to be. Let's get the presentation up. Is going to be from Dr. Robert Massey from the Royal Astronomical Society, who's going to be speaking on the Royal Astronomical Society working for astronomers and space scientists. So the Royal Astronomical Society is a learned society and charity which was founded in 1820, which works to advance the sciences of astronomy and geophysics. It also encourages and promotes the study of astronomy, solar system science, geophysics, and other closely related branches of science. They are our partners for our event today, so we are looking very much forward to their talk. So over to you, Robert.
Thank you, Alan. Let's see, first of all, if I can get the tech to work. Always the first challenge. Let's see, window. Look. Ooh. Like to record. I think this is all right. Sorry, it's prompting me to do something with my settings I wasn't expecting, but I'll just say yes. Right, okay, almost there. It looks like I've got to do a password enter, but fortunately that's screen blocked. There we go. Looks all right. Okay, I may have to quit and rejoin you according to this. I didn't expect this, sorry, because I think it's this is a relatively new laptop and it's just getting the settings right. So if I'll disappear for a second and then I'll come back in.
That's absolutely all right.
Okay, I'm back. Okay, now let's try that again. Window, right, there we go. Should be up and running. It's a simple, there we go. That seems to be all right. Can you see that?
Yes, we
Excellent. Good. Okay. Right. I think and you're not getting infinity mirrors or anything strange like that.
It's all perfect.
Good. Okay, right. Well, can't say further than that. Okay. Well, I'm just going to go to the presentation and thank you, actually, Alam, because you sort of you introduced us very appropriately there, and we're happy to have you. And I think a couple of other people on the call as members. So I'm not going to talk for an enormous length of time. I have to say it was quite interesting to join at a point where to hear the history of proposing the use of nuclear weapons for particle physics experiments. That was something I hadn't appreciated had been considered. And I agree with you just as well that you can't ever really properly divorce science and politics. And certainly in the UK, that's no exception. You know, we're always slightly naive to imagine that as, you know, something close to my heart given the era I work in. But yeah, I'm Rob Mass, I'm Deputy Director of the Royal Astronomical Society. And I want to tell you a little bit about our kind of foundation history, just thought, you know, a little bit around that, and then what we do today, and, you know, encourage you to join if it's the kind of thing that would be appropriate for you. So the title is, you know, what it says on the tin. We're working for astronomers and space scientists, but we also, you know, we represent solid Earth geophysicists, planetary scientists, people working in industry, authors, historians, teachers, and so on. So there's a wide range of members, even advanced amateur astronomers too are eligible to join. We just don't encourage every amateur astronomer because it's not the cheapest thing for them to do. So who are we? Well, we were founded 203 years ago, actually 203 years ago this month, I think, well, more or less. We're a learned society, which is a particular UK description, or certainly UK, US and European one, where they have scientific organizations that was set up in the 19th century with that description on the whole. In the UK, there are some older ones like the Royal Society and so on. We have around 4,000 members, all of whom are called fellows. And they're in about 70 countries around the world. The last time I checked, the majority are in the UK, as you would expect. And our mission, as Alam set out, is to encourage and promote the study of these sciences: astronomy, solar system science, geophysics, and so on. And our first president was actually a planetary scientist, William Herschel, most famous for discovering Uranus, also a talented lunar astronomer and so on, worked in Bath and Slough during his time in the UK, but originally from Germany. And the current incumbent is Mike Edmonds, who has a bit over, well, about a year and a half to go of his term. They serve 2-year terms, so he's still got some way to go with that. And he's an astrophysicist in Cardiff. And we are, I should stress, one of the things to understand about us is that we're entirely independent of government. You know, we're not affiliated or subject to those rules in the same way, but we are a charity, so we're obviously mindful of that. See if I can advance slides. There we go. I love to include this stuff just because it's quite fun. It's where we were founded, in a pub that no longer exists called the Freemasons Tavern, although the site does, on Great Queen Street. It's just over to the east of Covent Garden. And there are blue plaques for some societies there. The Football Association was founded there as well, apparently. And it was about 12 men, because that's exactly how things were in 1820, sitting down to dinner to discuss the foundation of a society, an astronomical society. And they included people like Charles Babbage, you know, famous for the difference engine, Bailey, who did some, you know, things like Bailey's beads and so on. And also, I go through to this slide, various other figures like John Herschel, William's son, and William Pearson here, who's, I don't think that well known, but he did, you know, various work in Leicestershire, actually, which was something that was dear to the heart of our president during our bicentenary 3 years ago. Emma Bunce, who's in the bottom left picture there, on a windswept day in the village of South Kilworth when we put up this plaque. That was one of the few events we managed to do in person during our bicentenary. And then I think the final bicentenary event was a parliamentary reception we managed last year, 2 years after it should have taken place. But, you know, so we have this kind of collection of individuals who wanted to establish an astronomical society, not all of whom are necessarily known for astronomy itself. And of course, at the time, it wasn't, with a few exceptions, it wasn't a professional science. You know, it was something done if you had the means to do so, which generally meant you were a wealthy, independent person of some means. A fair number of women, interestingly, involved in it at that time, because it wasn't considered as a paid occupation. So it was socially acceptable for women to pursue, not careers, but pursue studies in this area. So, you know, with that in mind, actually, some of the earliest contributors were women like Caroline Herschel at top center there. We actually named a medal for her in the last 2 years. And there's also a lecture that commemorates her as well, and so on. And, you know, there were, I'm only including this side actually just to demonstrate, of course, we've moved on a long way, but at that point around the time of our foundation, and really right towards the later part of the 19th century and even into the 20th, the kind of traditional ideas of astronomers as being people looking through telescopes and drawing what they saw at the eyepiece very much did apply, and that was, you know, very important in discovery science. So, you know, there are images even from the 20th century down at bottom right of Mars. It's only really, I think, in my lifetime, in the last 2 decades, that you've seen such advances in electronic sensors that it becomes possible to do a lot better than drawing through the eyepiece. Certainly as late as the 1980s, that was really important. You know, even with professional observatories struggled to achieve the kind of images that amateurs manage today. But, you know, this is the sort of stuff we have in our archives and so on, records of things like the, actually the Discovery of Uranus, which is before our foundation, but connected with our founding president. Images, you know, sketches of sunspots, a complete record over, I think it's spore record over 150 years, and then, you know, top right, a painting of a comet. That sort of stuff was very important in our early days. Now, obviously, I could talk about the whole history of astronomy and rapidly go through all this stuff. I'm not going to try to do that, but I do want to demonstrate that we have this interesting, quite illustrious history, and most of these materials as well are open to people to come and look at. You know, if you're one of our members or you're a guest and you want to go and look, that's absolutely fine. Our librarian's very open to that kind of thing. Much more recently than that, about a century after our foundation, this particular example I like. It sort of fits in partly with the last talk, but also it demonstrates the value of international collaboration, and sometimes that scientists are quite visionary in moving beyond immediate conflicts. So one of the other major things we did was to be part of a team or support a team that demonstrated the validity of general relativity. So and we had the anniversary of that in 2019, sorry. So Einstein had promulgated general relativity rather than special relativity in 1915. Of course, that was during the height of the First World War, so the discovery leaked out via neutral countries like the Netherlands, who were neutral in the First World War, and it was then there was a lot of interest in the physics community in the US and the UK and so on, even though, you know, at the time the UK was at war with Germany and later on the US was as well. And, you know, they had the foresight to prepare plans to test this. And one of the predictions you'll be aware of is that probably anyway, if you study physics, and if you're not, I'll tell you a bit about it, is that the conception that light travels in straight lines is true up to a point, but not if you have not in the presence of a gravitational field which curves space-time, curves the very shape of the universe. And that was something that could be tested. And the best way to do it was to look at the sun as a nearby strong gravitational source, look at a star near the sun and see if the sun's gravity shifted its position. Now, if you look at the sun in the sky, I don't recommend that obviously, but you would see during a total solar eclipse is the only time it's safe to do that, and during totality, and there would be stars nearby, and they would shift, their apparent position would shift if this theory was correct. And an expedition in 1919, so immediately after the First World War, actually before the Treaty of Versailles was signed, sent teams out to Principe, off the coast of West Africa, and to Sobral in Brazil to test it. And it was successful. It was a very marginal result, a very tough thing to do, but it did work. And we were part of the funder for that, along with the Royal Society. You know, quite a visionary thing to do, considering at the time the planning was almost taking place during the First World War as well, given the timescale to put it all together. And then more recently, we've not been in a position to fund large scientific expeditions anymore, although you know, we certainly contribute a little bit to that, and I'll tell you a bit about that later on after this. But we do make recommendations to government to this day, though, and visible demonstrations of that in the UK are things like the construction of the radio observatory at Jodrell Bank, which the RAS supported, but in a report in about 1947, and similarly large optical observatories in another report about just the year before, I think about 1946, and that led to the construction of the Isaac Newton telescope, which is small by modern standards, but was actually built in Sussex. The dome, which is all unfortunately unsafe due to asbestos and so on, is still the site in Hurstmonceux to this day, but the telescope is now in La Palma, and it was enormously successful out there, although I think it's still used for survey work and so on. So we have attempted over time to, you know, steer the direction of science and make recommendations as well. I think a more recent example might be things like assessing the scientific value of human space exploration, for example, which we eventually, the report that we commissioned on that did conclude that was a good thing to do, although there was an associated scientific value. It was quite a long time ago, so I don't know whether the conclusions would change over time. So what do we do today? Well, it's always the kind of list I have to write out and then remember to try and mention most things. And it ranges from the historic to the contemporary, as you might expect, given our history. So we offer, we have things like a historic library, what is described sometimes as a library of last resort, which sounds like a terrible title. But what it means is that you're able to access things through us that are maybe either not found at all elsewhere or very difficult to find. So we maintain a collection of historical astronomy books. We have things like a first edition of Nicholas Copernicus's tract, I'm not very good at pronouncing this, but De Revolutionibus Orbium Celestium, the one that, proposed in the modern era that the sun was at the center of the solar system. But there are others as well, plenty of things dating right back to the 15th century and texts from, well, certainly mostly European texts, but it's an impressive collection. And we get researchers coming in to use those either to do historical research or sometimes actually with things like sunspot drawings to feed that into contemporary scientific research, because those are the kind of records you need to refer to. We also pay for things like small research projects or travel grants and so on. That's a very important thing for us. And many early career researchers, like hopefully the majority of you on this call, have taken advantage of that. Travel to conferences is a big thing, but also things like seed funding. We paid for one of our former council members, Jane MacArthur, this was before she was on council, but gave her a grant to do some testbed work in Morocco with the Mars analog rover, for example. And then, of course, we also are advocates for these sciences too. So it's very important to us that we demonstrate their value, and we do that through things like assessing their wider impact and effect on whether that's on inspiration of young people, and particularly at school age, or whether it's on the spin-outs that go into industry and what it does for science and technology in the UK in general. And yes, needless to say, we do things like support, we obviously enthusiastic about things like the deployment of JWST, but also on our geophysics side, we're aware of the value of that science in assessing things like climate change. So, things like the Orbiting Climate Observatory down at the bottom right and so on. So we are an advocacy body as well. We also do things like, as you would imagine, publish scientific journals, offer a magazine to our members, and host a whole load of scientific meetings too. That's really important to us. I didn't mention this in the previous one, but yes, some of the things we fund student travel to conferences, as I said, but we also fund a couple of research fellowships, so basically jobs as well. Can't do any more than that, but at that sort of low level, we're there to help a little bit, and certainly those have a large number of applicants. It seems to be a very popular thing. I should mention as well, we do a lot of public engagement work. The highest profile thing, I think, would be things like our RAS 200 Sky and Earth project, which put about £1 million into that area over about 8 years or something like that. It's now coming to an end, and there'll be a big meeting on it actually next Friday, as it happens. If anybody's interested in going to that, if you're one of our members, you can go for free. Otherwise, it's £5. It's not an expensive thing to do. And we, but we fund ad hoc things as well. So that Deep Space High thing there's Fun Kids Radio, which I wasn't even aware of until they approached us for grant. We funded a series on astronomy for them as well. And the example at the top right, by the way, is the Tactile Universe project, which is for visually impaired people to access astronomy. So some of the things I've already referred to, but so it's easier to remind yourself of these things in pictures. Library at top center I've talked about, but I should also, I don't know if I've got a good picture, I should have included the Burlington House. Premises, you are, as a fellow, able to book meeting space there. We don't usually charge our fellows unless there's a, except for catering and so on. We don't allow you to say book meetings up for 10 years, but if it's within about the next 3 months, you could book a space for scientific meetings. There's no problem doing that if there's availability. And that's a valuable asset in the middle of London while we have that. We give out awards and medals. That's what looks like those coins at the top right are, but they're actually a series of medals we award for different things. And they range from, obviously, as you would expect, excellence and research through to things like public engagement and so on, and sort of services to astronomy. And it covers all manner of different aspects of the work in the field. and they cover geophysics as well. I've already talked about the fact we do public engagement, but that continues, that's something that was very big in the run-up to our bicentenary anniversary, but we don't expect to roll back on it. And in fact, the meeting we're holding next week is discussing that strategy as well. And scientific meetings are a really important thing for us. It's been said actually that there are very few learning societies that run quite the program we do. I guess actually UKSEDS is almost an exception because it's so active. But we hold 6 or 7 scientific meetings on our premises each year, and that's doubled up because that's 6 or 7 dates. So half of those are designated as A, or astronomy, although it's quite a loose designation, and half of them as geophysics, which, as I think I said at the outset, includes planetary science. So we do have a lot of things going on, and it is a good way to disseminate work. And let's have an annual conference actually, which this coming year will be in Cardiff in July. That we that's generally a major event for us. And it's actually pretty well attended. Last year in Warwick, I suppose, in the bounce back from the pandemic, they were getting on for 700 odd people there, and then another 150, 200 online. And then I should also mention we publish scientific journals. So monthly notices, the RAS, a complete misnomer because it's not monthly. It's not really about notices. It's some scientific papers, and they're out all the time. I mean, typically they're released about 3 times a month because the field is so busy and it takes papers from all over the world. If you're a member, if you're one of our members, you can access all those for nothing as well. And then we publish this bi-monthly magazine, A&G, that covers different reviews and news stories in our field. So a few of the things we've been doing recently, these are some highlights in 2022. So we did things like we launched a new journal there, Techniques and Instruments. That's an open access one. We're moving into that domain and opening it up with journals like this. At the top right was one of the bicentenary projects. If you're wondering what that was, it's a JWST quilt that was put together by my former colleague Annie Hogan, which has been really quite something. At the bottom right, Caroline Herschel medal I mentioned before. That's an Anglo-German initiative. So it was actually, I think it was at the instigation of Carol Mundell, who was the former chief scientific advisor to the Foreign Office, and she is an astronomer. She's now gone off to work for the European Space Agency as a director there. She mentioned my colleague Sheila Kanani. Some of you may know, won an MBE for her work in public engagement, to add to a couple of other medals she's already received. And even though we had challenges, I've just noticed actually that Weird and Wonderful World of Uranus dates in 2021. Never mind, I'll find a more up-to-date example. But even though we had the challenges associated with the pandemic, we were able to engage very successfully by putting on various live stream events that had huge audiences actually. I mean, you wouldn't think that a bunch of astronomers talking about infrared spectra from a telescope in Hawaii about Uranus would be as popular as it was, but it really was thousands and thousands of views. And on that, to the bottom left is our supermassive podcast, which that's episode 29 there. I think we must be up to about episode 40 now. That has been running for 3 years, and that's up to about 650,000 downloads. So we have a nice audience for that too. Do check that out if you haven't. It's entirely free. So I should mention, though, the other things we're kind of doing for the community are in the policy and politics domain. I'm fairly partisan in my private life, but not in this. We try to be objective about how we understand the issues that affect our sciences, and there's a fair number at the moment. They're only slow to change, so I would have been saying much the same things last year. One of them is the ongoing post-Brexit relationship between the UK and the EU, and things like whether we actually associate with Horizon Europe, which wasn't resolved last year and still isn't resolved at this point. I don't know whether it will be in the near future or whether it's now completely unlikely, and certainly the details of any replacement haven't been announced. That matters. If you're an early career researcher and let me get back one. If you're an early career researcher and you want to move into Europe or move into larger collaborations, it has been a natural route for that. And it's unfortunate that although there's a compensation scheme, it's rather more difficult to access at the moment. Ukraine, that's been obviously, clearly the human catastrophe there is you know, I'm not going to pretend that the impact on astronomy and geophysics and planetary science is the most important thing by any means, but there is one, and we've been thinking about ways in which we can support researchers and scientists who are affected by that as effectively our community out there. Not a huge number of people, but we are trying to do that where we can. So if anybody knows anybody who might benefit from our help, then let me know. There's the enduring impact of COVID. Now, by that, I'm not just thinking about the people who have, say, things like long COVID and so on. We're thinking about what it actually did to the research community. And there's evidence, for example, that it might have hit women as primary carers and families harder because of the fact that schools were closed, and as that kind of example. And we're trying to understand what that's done. And also the impact on, say, PhD projects, for example, was not great because they were interrupted in some cases. And it's not been ideal. We're interested as a responsible organization in how we make our science more climate friendly, so moving to net zero. We signed the Climate Neutral Now declaration last year, I think it was, and we've sent in reports on monitoring our carbon footprint. I'm personally very committed to trying to make that improve over time. It's got its challenges because the nature of the building we're in and the kind of way in which scientists work through long haul flights and so on, but we're determined to get better on that. And there's other work going on from my colleagues in areas like workplace culture. We'll have a report coming out on that in a couple of months' time. It's not entirely great. Some of it's fine, some of it really isn't. And I talking about areas like bullying and harassment is a priority for us. We don't want to shy away from that. The lack of diversity in the field remains an issue. We're in the process of doing another major demographic survey, which if you're on our list or you're in some ways contactable through being a member of the astronomy or geophysics community, then you might be getting a survey from us in the near future. And if you feel able to respond to that, please do, because the data is incredibly useful. Nobody else is going to collect it. Basically, we have to do that work ourselves. And then finally, some of the stuff that's been in the news recently is around the impact of large or huge satellite constellations and what they do to our science, and the wider realm of space sustainability, so areas like space debris and so on. There was Lucy Green on Radio 4 this morning talking about this stuff. I could also add in, actually, that very recently we've started doing more work again on light pollution on the ground as well. Just really in the last few months, we've signed up to do that stuff. So if you're interested in some of this stuff, I think the thing about the RAS, like many societies, I'm sure it applies to UKSEDS as well, is you sort of get out to some extent what you put into it. Even if you join and you just come to our meetings and keep yourselves up to date with the field in general, I think that's a valuable benefit of membership. But you can also do things like, apply for grants, sign up to our journals, run for our governing council if you want to. And there's also, it'd be remiss of me not to mention the Early Career Network that's doing really well, that's been running events for people who are either our students, postgrads, postdocs, to advise them on their next steps. And that was an initiative. Well, we supported it and fostered it, but it's basically an organization that's run by early career researchers themselves. Not trying to compete with UKSEDS, by the way, but just to mention that it's there and it helps shape our thinking. And I think is a reminder for our more established members, say, of our council, that this is a community we need to support. So if you'd like to join us, because I have to add in this plug at the end, obviously, we have a cheap introductory rate for students. It's only £5, £30 a year thereafter. This is obviously, as you can imagine, if you pay by direct debit, you can, we don't keep people for life. If you move out of the field completely and you no longer wish to be a member, we're not in the least bit offended by that, although obviously we like it if you stay. You can find out more about that on our website, and also our social media accounts, which are pretty active on the whole, thanks to my colleague Gurjeet. So, you can always find out more about the kind of work we're doing, the things we're supporting through that route as well. Now, I think that may be my last slide. Am I right? Yes, I am. So I will tab back to where I can see you and stop sharing my screen. There we go. Excellent. So if anybody wants to ask anything, that's fine. And otherwise, I'll leave you to continue with your meeting.
Thank you very much, Robert, for telling us about the Royal Astronomical Society. I mean, I'm personally a fellow. I know there's some other fellows right now in the meeting, and personally, I've been attending the meetings now for about a few months, and actually, I've been surprised about how welcoming the whole group is, considering the fact that there is a considerable amount of undergraduates that have started attending. So, does anybody have any questions at the moment? Okay, there seems to
I have
be
one quick question.
Okay, go ahead, Isha.
This is just generally about the society, actually. So my name's Isha. Lovely to meet you. I'm currently the president of KCL Space. I've yet to turn up to one of these ordinary meetings. Because I've been busy in the last few months. So hopefully I can come to the next one. But I just wanted to know how the RAS could support societies in terms of, I know there's some room bookings availabilities or just general events, or is there any other way that RAS could generally support societies, space societies specifically?
Well, look, I mean, the answer is that if you're one of our members, you can book rooms. I mean, the prioritization of that will be, look, we're going to support rooms that are associated with science, or bookings that are associated with science, because that's closer to our mission. So if it fits into that, then that's fine. I mean, I'm not sure what the demand is at the moment. Historically, it was very high, as you can imagine. And then, of course, the pandemic of 0, and now it's building up again. But, you know, in principle, there should be no reason why you say can't book our council room or our lecture theatre. I'd have to check in with my colleague Richard about all the details of that, but plenty of groups do. I think the only time it tends to, you know, they'll have qualms about it is if, say, we have had things like, I don't know, you get a private company that's completely unconnected, where one of their staff is a fellow and tries to book the room for the company and all the rest of it.
Right.
And we think, well, actually, ethically, you know, that doesn't really fit in with our charitable purposes. But it's, you know, frankly, it's, I think we'd want to encourage it. You know, if you've got something like that, that'd be valuable. I mean, even if you're having, say, some space-related speakers, it's close enough to our mission, I think. Don't take this on trust from me. You know, you'll have to go to my Richard's check. But you know, yeah, within reason, we try to be welcoming. And if you're not a member, then join and do come to our ordinary meetings and things. You know, they're actually, I didn't mention those, but they're good because they're supposed. I mean, they're not lightweight, but they are intended to be more general. So if you want to come in and find out just out of interest what's going on in the field of those general, I think I like them for that reason. I think they're really good. You know, it's and they're perhaps we haven't got a lot of stuff right on our website and the way we promote them, and I think they're underappreciated. So I definitely encourage you to come. And you know, and it is a chance to put questions to some absolutely world-leading people.
Yeah, definitely. And I was also wondering, quick question. You mentioned how you used to do tours and stuff like Jodrell Bank and stuff. Do you still do that, like trips around to?
Oh well, okay, yeah. Did I? I can't remember mentioning that actually, but I think, well, the context of that, if that stuff where it happens is connected with our friends organization, actually, which is a sort of different type of member, and they go on those kind of events. I should say, actually, it's not that hard to get onto tours of places like that anyway, because Jodrell Bank is quite welcoming, a nice open place. We're not generally doing it for all our fellows because actually they tend to access that stuff anyway. But the Friends group does that, yeah, if you're interested in that. But I mean, it depends on the kind of category of membership you want.
Okay, perfect.
Thank you very much, Robert. And we're going to be going on a break now. So after our break, which should be done at 1:30, we will be having Amy speaking on. We'll have Amy speaking. So we'll see you all at 1:30.
Thanks, Alam. I'll see you. Well, wish you. Hope you all have a good afternoon. Thank you.
Thank you
very much.
Really informative. Thank you.
Hello? I just wanted to check that you can hear me.
Yes, we can.
Yes.
Okay. That's progress. If you can still hear me. Ninja.
Yep.
Affirmative.
You're bringing the slides up? So my laptop is just sort of spinning. It's just slow, I think, today.
Oh.
I checked whether it was trying to do an update or anything, but that's not the problem. I don't know. I don't know what the issue is. What we need, if that's all right.
Yeah. We are going on a break for just about 15 minutes. But the slides, yeah, the slides seem to be working. Yep, I've tried them.
Okay, that's fine as long as you're happy. And yeah, I was just checking during the break that you can hear me, so I won't touch anything between now and then, and then hopefully all the technical challenges will, you know, we'll work around them.
That's perfect. Thank you.
Welcome back, everyone. Now, after the break, we're starting our next talk. So next up, we have Dr. Amy Riches. She's a managing editor, freelance scientist and hobby writer, and she's a visitor at the Earth and Planetary Sciences Institute at the School of Geosciences at the University of Edinburgh, and is also an affiliate scientist at the SETI Institute in the US. She'll be giving a talk on building worlds, what can meteorites tell us about rock and body histories. So I'll hand over to Amy now.
Thank you, Holly. So I think that someone else has got my slides there. Great. Do you want to put that in presentation mode? Great. Yep. So I'm here to talk about how we understand the construction of worlds, in particular rocky bodies, and the role that meteorites play in how we decipher those histories. So you can see here a couple of images on the front that just show you the types of meteorites that we have, and they're still falling to Earth today. So we have the Peekskill meteorite, which, as you can see, hit a car when it landed on the Earth. That's a chondritic meteorite. And then also the Fukan palisite, where you can see it being held up there. Meteorites are sometimes popular among collectors. So we kind of have a relationship with those where it's nice if people work with us as a scientific community, but sometimes occasionally we lose meteorites to collectors. And you can see the light shining through those olivines in orange there, and then there's metal woven in between. So in those cases, we might think of those as an analog to a core mantle boundary within a rocky world. Yep, so next slide. So first of all, obviously, if we're going to look at rocks from space, we need them to get here so that we can study them. So some rocks that we study fall to Earth. When they're traveling through Earth's atmosphere, they're termed meteors. When they actually land on the ground, they become a meteorite, which we can potentially collect or find at a later date. So here we've got an image of a fireball. So you can see the meteor entering Earth's atmosphere. And in some cases these days, obviously, we have, you may have heard of fireball networks, which are the video cameras spread across the, well, many nations and across the world, essentially. Those help us track and recover meteorites, and to also look at the trajectories to understand where some of those have come from. So there are only a few of those. Most meteorites are actually finds. So next slide. So the overall concept that we're dealing with when we study rocks from space links to two broad areas. We can look at fundamental questions, as I've mentioned, how planets can form. That's an example for you. But we can also link our studies to the actual exploration of space, so to mission science, be that rovers, remote sensing data, or other forms of exploration. And of course, where we need to know about the physical properties of the rocks on bodies for exploratory purposes, then we could potentially help to reveal that, to constrain that information that engineers might require. So if you click the next button, when we're dealing with fundamental questions, of course, those range very broadly. We might, as a geochemist, as I am, someone who looks at the chemistry of the rocks, we might group those into two broad areas, such as low temperature processes. So in that sense, we're often considering things of a few hundred degrees C or less, or high temperature processes, so that involve with melting rocks, so 900 degrees Celsius plus, for example. And then there are other forms of high temperature processes that we might potentially track that are linked to the earlier history of a nebula. To the next click. So when we're looking at, particularly from data from space missions, and linking that to some observations from our samples, we might be looking for present day signals or the relatively recent past. And then obviously when we're trying to track how planets are formed over many millions and billions of years, then we're looking into deep time. So we're looking at the past history, which can be difficult to decipher, can have multiple aspects to it. So we need to unravel all those different pieces of the history within the individual rocks and within the rocks from space as a whole collection. Next slide. So just to So people who come into studying rocks from space will come from many different backgrounds in terms of the subject areas that they've worked on before they perhaps train in planetary sciences, potentially at master's or PhD level. I came from a background of geology, and within the geoscience or earth science frameworks that we have available to us, we often think of planetary processes under 4 broad spheres that are interconnected. The hydrosphere, obviously dealing with the watery parts of the world, the atmosphere, and the biosphere, where we have life. And the geosphere is obviously a very big part of that and connects with all of those other aspects. And this is really the area that we focus on when we're studying meteorites. Next slide. And of course, we're considering solar system science. So while we may primarily look at rocky worlds such as Mars, Earth in the inner solar system, we don't have meteorites from Venus that we know of, and we don't have confirmed meteorites from Mercury either. But we have many samples that we consider to derive from the asteroid belt, which sits between Mars and Jupiter. So it gives us an understanding of what's happened within the inner solar system for sure, and then we can try and make inferences about influences from the outer solar system, which is primarily studied at this stage through missions. So next slide. And we can often link the observations that we have from solar system sciences to the broader understanding of how solar systems work. Is our solar system a good example of others, or are they all very different? What aspects are common and what aspects differ? And so, for example, astronomers will study different solar systems, and if we're very lucky, we capture things such as the moon forming disk appearing around a Jupiter-like planet, as was seen in 2021. But overall, we're trying to put the puzzle together to understand if we've got rocky worlds within our own solar system, and we know that on Earth we have life, does that apply elsewhere? And will worlds that are able to support life have followed a similar path to Earth, or could they have followed a different history? Next slide. So in terms of how we study rocks, we can look at processes such as impacts, for example. Meteorites have fallen to Earth. In doing so, obviously, they have impacted something. They've hit the ground. Now, depending on the size that they are, that determines what happens to the sample when it hits, but also, it has an impact on Earth. And of course on other bodies too. So they have a heavily cratered surface on the moon, which we can link to as a means of tracing the very ancient history of Earth, because obviously we've erased quite a lot of the surface history of Earth through subduction processing and mountain building and weathering and other processes. But impact craters are also tourist attractions, so they can be important to local economies. And we also know, obviously, you want to be quite aware of what is in your meteorites, because people are beginning to infuse wines and cheeses with them. So you want to think carefully about what you're eating. Next slide. Thanks. And so one example of an impact crater is, of course, the Chicxulub crater off the Yucatan Peninsula, or overlapping with the Yucatan Peninsula. So this is actually a submerged crater. So it's been detected through geophysical methods as a large circular feature with a peak in the middle. It occurs around about 65 million years ago, around the Cretaceous-Paleogene boundary. It's a large crater, so it's 180 kilometers across, 60 kilometers deep. And the impact was incredibly energetic, so 200 more times energetic than the largest ever detonated man-made explosive device, which are, of course, our atomic bombs that went off. Next slide. There are consequences, and in this case, next click. Dinosaurs, of course, we know were wiped out, so we had significant environmental disturbance and with ecological consequences. Next click. Leading to a mass extinction at this time. So this is one area that's important for as a means of understanding the meteorite history of the Earth, so understanding the bombardment history within the solar system, as well as understanding fundamental questions about how planets are formed. Next. So in terms of looking at how planets grow, we often consider accretion, which is the processes by which things are brought together at different phases of planetary growth, be they ices or rocks, because we want to understand the origin of Earth's water, for example. Next slide. Next slide, please. In terms of understanding accretion and planetary growth, we want to look at the age constraints we have. So how old is the solar system itself? You know, what are the oldest materials that we can date within the solar system? An example of this is calcium aluminium inclusions, which tend to be these sort of white fluffy features, which are rich and, as the name implies, in calcium and aluminium, and these are found within chondritic type meteorites. They're a specific type of meteorite that have not undergone a high degree of melting, and these inclusions within them they condense at high temperatures, and so they give you ancient ages because they were some of the first things to form as the cloud of nebular gas and dust was cooling very early on in the history of our solar system. So the example given here is one of the oldest dates that's available at 4.567 or 8 billion years ago. Next, click. And this really gives us a constraint on what was happening and how quickly primitive bodies were coming together. So by primitive, we mean these unmelted bodies, the sort of conglomerates or rubble pile bodies. Next, click. When they become large enough and hot enough, those undergo melting, and as a consequence of which you begin to segregate out different things. So the metal, iron, nickel metals might go to the center or coalesce together to form iron, nickel, sort of core or core analogues, and then you might have a rocky mantle-y material around that melted material, and on top of which you might have sort of a crust, which again could be rocky, it could be of a slightly different composition to its mantle. Next, click. And ultimately, of course, these grow into larger bodies, and within our own solar system, the present day, we have the Earth-Moon system, and obviously on Earth we have ample water at the surface and we have life. So this is really important to understand what happened between those two different points. So next, click. So my own area of work tends to focus on the formation of those bodies as they were growing. So before we got to the size of a full-scale planet, how did we get there? Trying to unravel that part of history of the Earth-Moon system. Next, click. So really, meteorites don't give us a complete record of the history of the solar system. So these are sort of the leftovers, but a lot of material has already gone into planets to form them. Some materials may have been ejected from the solar system. And so you're really doing a sort of detective work on this. It's a little bit like forensic science, and you have many questions to answer. So understanding the composition of the meteorites and other physical features about them, and then how those features match up with various constraints from different areas of modeling. So next slide. So to get our hands on rocks from space, as I said, many of them are finds, some are falls, but many of them are finds. And when they are found, often we rely on, or one feature that we rely on is the contrast in color. So meteorites, when they come through Earth's atmosphere, they develop a fusion crust that gives them a dark outer coating, which will contrast to environments which are lighter in color, such as cold deserts, such as the Antarctic. If you click, something else will pop up, and also hot deserts, such as shown here, a picture provided by Malaka, which is of the Atacama Desert over in Chile. So next, click. We can also, of course, study materials that are returned to Earth directly from space missions. So an example given here is China's recent Chang'e 5 mission, which has brought back materials from the moon. We obviously had materials returned from the moon through the lunar and Apollo missions earlier in human history, and we've had some samples returned, from comets and asteroids, and we're going to be hearing a lot more about that, I think, in future through the community. So next slide. There are many, many different types of meteorites, so I don't want to go through them all. I just want to mention to you that there are lots of different types, and they each tell you a different part of the story in terms of the history of the solar system. And some of those meteorites are linked to certain bodies, such as Mars, a particular 4 Vesta asteroid for what's termed the HED group, which is a Haradite, Euclidite, Diogenite group of meteorites. And obviously lunar meteorites are linked to the moon. And then there are other types of meteorites for which we don't know where their original body is. We have some theories, some suggestions, and we were yet to sort of be sure of where they came from. So in those cases, we term those parent bodies, so they might be, and we often put the name of the meteorite in front of that when we're talking about these. So that in terms of when we start to get into technical language, that's how we go about it. Next slide. So to look at the science within meteorites, how do we extract the messages that they contain? Well, we have to look at them to begin with. So as someone who was a geologist originally, essentially we're applying similar techniques. We're looking at things under the microscope to see what's there. And we can also, I'm just going to mention here that there is a virtual microscope which has a catalogue within it of various different meteorite samples, some of which are Scottish, some of which are lunar materials, and you can look at all those different types of rocks. So even if you can't look at them in the lab, you can have a look at some things on the virtual microscope, which is a really important resource. Next, click. We can also acquire maps, compositional maps of our samples. So not only can we look at these under a typical cross-polar and reflected light microscope, but we can also look at things within, for example, instruments that map the different compositions. We can then generate what we call a false color map, as shown in this image, and that we can label that up to show different minerals. So orange is and greens and sort of lighter shades there show different mineral phases, which can be really important. And we can look at different textural zones. So you can see on that particular sample that we've got A, B, C, and D areas. And those are different textural areas. So then we look at the relationships between those, try and decipher why they're different, and how they've come together. So next slide. So in looking at the composition of the minerals in the first instance, this can actually give us a way to confirm that a sample is a meteorite and to group it with other meteorites. So you can see here that there are different slopes, broadly defined slopes for different meteorite groups. So there's a slope for the Earth in terms of its iron and manganese within the pyroxenes, a different slope defined for that of the Moon, Mars, for example, the HED group meteorites linked to the 4 Vesta asteroid, and Angrites, which are a particular and quite special kind of meteorite group. And that can be really useful, not only for grouping things and deciding which group things belong to, but also for starting to understand the conditions under which these samples have formed. So in all cases here, I'm just going to emphasize that these are all achondrite meteorites. So these are all meteorites that have undergone melting. Next slide. Right, so we can also build on the elemental understanding. So looking at the composition of the minerals, we can look at the trace elements within those. So here, there's sort of a range of rare earth element profiles shown for samples from an Angrite meteorite in particular here. But just to give you an example of what work we do on these, and then we can compare the mineral compositions to what we term bulk rock. Often we have a powder which is from a very small fraction, so it's quite different from working on geological samples. So we often have to try and reconstruct a bulk composition from the minerals and compare that to what we have from a small powder fraction, and make sure that that powder fraction is representative, or discuss why it may not be for the whole meteorite. Next slide. We can also a key step in identifying meteorites and then working on them is looking at the oxygen isotope composition. So this is stable isotope ratios. We're looking at 16, 17, and 18 oxygen, and their ratios relative to one another and relative to a reference material. And you can see that we have different slope lines, and then we kind of look at the cap delta 17 value, and you can see that there are different groupings there. So there's a Martian fractionation line. So if meteorites are from Mars, they tend to group together along the Martian fractionation line, which is really exciting if you find a new Martian meteorite. We have a terrestrial fractionation line. So that's essentially grouping for the Earth and Moon. There is some very recent data which sort of looks at small differences, but I'm not going to get into that here. Angrites, again, they group and tend to follow a broad fractionation line. And again, the Haradite, Eucrite, Diogenite set of meteorites, they tend to group together in terms of their oxygen isotope compositions. So that's really helpful. It tells you that they're related. It tells you that they may be from the same body. So then we can treat them as a group and start to decipher what's happening with that whole body. Okay, next slide. So in terms of then taking these rocks apart, we know that we can look at minerals. We can use things like an iron microprobe, such as we have at Edinburgh. We can also do wet chemistry work on powders for the rocks, but also to some extent on minerals if we drill them. So with a very small drill, and using essentially a dental drill tip, and you can then digest those materials. Depending on the type of chemistry you're doing, you can potentially digest them using mixed acid and on a standard ventilated hot plate, or you might, if you're doing my kind of chemistry, you might need high pressure and high temperature to confine those samples while they're digesting. So that can be quite fun. And then you put them in a really fancy mass spectrometer to look at high precision isotope ratios. So it's great if you get to work in a clean lab, then can be quite a therapeutic working environment. And then you get some really nice, highly precise data. It can take quite a while to get this data, but once you have it, it's great to have that data and then think about what it all means. So the next slide, please. So in terms of what we're doing when we're doing chemistry, be that elemental or isotopic, and when we're dealing with isotope ratios, whether we're looking at stable, radiogenic, or nucleosynthetic signals, we think about where the elements group, how they behave. That's also a really helpful starting point. So what's common in the geosciences is that we have the Goldschmidt's classification, which describes elements that that like the silicate minerals, the rocky minerals, the lithophile elements, whether they like the iron or tend to go to the core if you're thinking about a large planet. So hydrophile elements, whether they like the sulfur, so if they're chalcophile, or whether they tend to prefer to be atmophile elements. But of course, one thing with the periodic table and Goldschmidt's classification is that it's very Earth-centric. So next click. When we're thinking about planetary science, we might reference the cosmochemical periodic table where we have use for that. And that really talks about or speaks to the way in which elements condense out over a solar nebula composition that's analogous to our solar system under certain conditions. So if they're refractory, these are the elements that condense out at high temperatures, so they condense out first. And then obviously as we move to the right, we end up with highly volatile elements, so those that condense out later, and they tend to be more gaseous in terms of an Earth-like environment. So yeah, we can think about elements in different ways. Next click. We can also plot these what we consider to be the bulk composition of a planetary body, and then we can take what we call a comparative planetology approach. So we look at the different abundances within different bodies. So the dots shown there and the broad grey bars mark Earth's trends. It tends to be on the right hand side there. You can see sort of a flat line across for the majority of elements at 1, and then there's a slope down, which, and the mechanisms that may cause that slope could be due to the loss of elements which have some volatility to them. It could be due to sequestering some elements in the core, or it could be that you've originally formed the Earth from materials that lacked some of those elements. And those are long-standing questions to resolve. And then we can see by comparing them to, for example, Mars, there's a different slope on the left-hand side there, and other bodies such as the Angrites parent body, which is this unusual group of meteorites, they again have a different slope. And you can see that I've circled a set of elements there on the bottom right, which we term the highly cytophile elements, and they're really exciting to study, or I think they are, for specific reasons that we'll briefly look at. So yeah, if we move on to the next slide. Yeah, so we can look at other aspects of the samples. So while the previous slide showed that we can sort of decipher bulk compositions and that can tell us something about how a planet formed, we can also look at signals within the samples that may give us insights into the surface conditions on a planetary body. So this is an example from a student study led by Nicola Murray, where he looked at the sulfur isotope composition. So looking at individual sulfides via ion microprobe techniques, so looking at these with a beam. And the range of values that we see, we could compare to rover data from the surface. And also we can make inferences about where those signals come from. And it really tells us that we were looking in that case at those samples at an extraterrestrial volcanic edifice. Then we were trying to, work out which way up the samples were. How did we stack those meteorites when they were first blasted off the surface? And also, looking at traces of surface and atmospheric composition. So for a body like Mars, that's obviously really important for understanding the potential for life there, in terms of the recent past and also the current day. Next slide. Right, so I mentioned those elements in the bottom right-hand corner, the highly cytophile elements. So these are iron-loving. Next click. So we're dealing with a suite of elements: osmium, iridium, platinum, palladium, ruthenium, rhodium, and also we include rhenium in that grouping. Rhenium is linked to osmium through radiogenic decay. So next click. What's helpful about these elements is that they have very high partition coefficients, so they love the iron. Next click, please. Next click. Yeah, and because these elements really love to go into iron nickel, when you're forming a large planetary body, they will tend to go to the core. Next click. To the degree that you end up with a highly depleted mantle relative to starting materials such as chondrites, which are the rubbly materials formed early in the solar system. So if we were only seeing core formation, we would strip from, for example, the Earth's mantle, all the highly cytophile elements to the point that we would not be able to measure them, but we can measure them. So that tells us something. All right, next click. Not only can we measure them, we can look at fractionation trends, for example, relative to magnesium oxide in a bulk sample, which if where these samples are achondrites, so melted rocks, and the shape of that can help us to predict the abundance in a mantle, which we may not sample directly. So essentially, also if there's any difference between different bodies, so is the amount we see in the mantle for Earth, Mars, and the Moon the same? That's really links to the image on the left, trying to work out how dilute these things are or not. Next, these are the ultra tracer levels. And I'm just going to really jump to why this is important. So if these studies are, current understanding, if that's correct, and if the study approaches we've taken to determine that data are appropriate, then the asteroid belt may potentially have either never significantly been more massive than today, or it rapidly lost more of its mass early in the solar system history. So this is a really big statement to make from a relatively limited amount of data for highly cytophile elements in a specific in some groupings of meteorites. So we're using that to talk about mass loss or not over the history of the solar system. Next button. Oh, back a bit. And it leads to, and there are all kinds of other papers on this subject. So, we could talk about tracing how planetary bodies are formed over the whole history of the solar system, and that, being a common process of impact. Just as the nature of growing planets. And then we can compare the relative abundances within different bodies to talk about the highly cytophile elements are really helpful to infer the mass percentage that we're adding to different bodies. The next slide, which is summarized in this figure on the right. If for Earth, for example, if the highly cytophile elements give us a signal after the formation of the core of the very last material that's added as the Earth was growing, and the composition of that material at that stage is, really important to infer. Did it bring water or not? So that's really interesting. And how much are we adding to the Earth relative to Mars, and when did we add it? Those are all important things. So next click. There are some assumptions that are made in terms of the fractionation trends in order to infer the mass amount. So this is really an area that I think deserves some further attention in future. So I'm not going to go into great detail about that, but you can see that there's a slope there, and we use that to infer the absolute abundance of highly cytophile elements within a mantle of a given body. But how robust that approach is something we're always looking at. Right, next slide.
Hi, sorry, Amy.
Yep.
We're in the final 5 minutes.
Yeah, this is the end.
Okay, thank you.
Next slide, if that's all right. I think it's.
Yeah, sorry, it's just a bit delayed sometimes.
Yeah. And the consequence of which of looking at these elements is to look at the overall architecture of the solar system, and from that we link to those people who work on the dynamics of the solar system, so people who use high power computers to develop models of how planetary bodies have moved within the solar system over time, particularly the gas giants and their influence on the distribution of materials in the solar system and when that may have occurred. So I think the next slide is the end slide. And I did some work on the 4 Vesta asteroid as part of a Marie Curie fellowship, so that's forthcoming. And the next slide is the end slide. Thank you. Those are just 2 databases of compositional data for meteorites. I just thought I'd mention that. Any questions?
Yeah, I do think actually we have some time for questions if there are any. If there aren't any now, that's all right. We can email any questions afterwards if we do receive any in the chat. But thank you very much, Amy, for your presentation.
Yeah, thanks for having me. Sorry for all the technical glitches today, but thanks for supporting that.
No worries at all. It seemed successful. I don't think anybody realized what was going on behind the scenes.
Great, but rocks from space are really fun to work on. That's the overall point, hopefully, to take.
So this presentation is going to be more about UKSEDS, as we briefly introduced back in the beginning. So our question is, who is UKSEDS? So we're a student organisation, a charity. We provide students with the opportunities to develop their skills, and we represent students who want to go into the space sector and support events to promote the understanding of space and its importance to life on Earth. So what does specifically UKSEDS do? So we're a charity that's run by student volunteers for students. We were formed in 1988 and we have over 1,000 members and 47 affiliated branches as of right now. Our aim is to connect students and the recent graduates with the space sector, and we improve the knowledge base, skill sets and hands-on experience levels of students in the UK with an active interest in space. We support multiple events during the year, our most popular being NSSE, which we hold every year in March. And at the end, we'll be discussing that with a lot more detail, as well as releasing some discount codes for the event. So what is the benefits of becoming a UKSEDS member? So we have the opportunity as UKSEDS members to access our community hub and Discord page to speak to other people in not only our own region, but across the country. We give you the opportunity to volunteer with us, whether it be in any of our multiple sectors. Our members will automatically be signed up to our monthly newsletter called The Elliptic. And you get access to valuable contacts and opportunities that are only exclusive to UKSEDS members. The biggest thing is that the membership for UKSEDS is free and easy, and we'll be providing links on how to get this. So the branches that we have, like I said, 47 branches across the country. And the benefits of that include having access to project grants to use on a multitude of different projects, which include the National Rocketry Competition, which we'll mention in a bit more detail later on. And yes, with that, I'm gonna hand it over to Holly.
Great, thank you, Alan. So talking a bit more about UKSEDS membership opportunities. So if you're no longer eligible for membership, so that will be up to 3 years after you graduate from a university course or apprenticeship, you can join our alumni network. So our alumni network are a valuable part of the work we do at UKSEDS, and there are many benefits to joining. So you can join a network of other UKSEDS members, so keep in contact with people you've worked with before, meet people with like-minded interests, and also talk to current UKSEDS members as well. You can gain access to exclusive events, become a mentor for our current UKSEDS members or our competitions, and also become a member of many other exciting upcoming projects as well. Next slide, please. So as I previously mentioned, to qualify for UKSEDS membership, you have to be a student at a university or undertaking a technical apprenticeship, or have graduated within the last 3 years from either of those. We have a new website, which we'll talk more on in detail about in a minute, where you can sign up for membership, and there's lots of information on there and opportunities to get involved with UKSEDS. Next slide. So as I mentioned, we've recently launched a new website, or the UKSEDS Community Hub. So this website contains information about upcoming events and competitions we run, and there are also some features on the website that are exclusive to UKSEDS members, such as forums and workshops. So we really encourage you to sign up, and we'll provide you details and various emails. Then you'll get an email by your branch, and we'll also have some posts on our social media channels about it as well. Next slide. So some more opportunities to get involved include taking part in our competitions. So I'm the competitions lead, so I'm quite biased towards this area, and I really encourage you to take part if you've not heard of this before or haven't taken part previously. We run 5 competitions on rocketry, satellite design, rover design, and in-orbit servicing and manufacturing. And each year we open registration in October on our website, and our competitions run through the year to July, and through the year you'll take part in various report or presentation stages that emulate excuse me that emulate industry practices such as preliminary design reviews and critical design reviews and test readiness reviews. We partner with industry in our competitions, so we're sponsored by companies including Airbus and Inmarsat, and they help guide our competition requirements and help us in running workshops to help everyone taking part in competitions develop technical and soft skills to boost their CV and future career opportunities. Next slide. So I'll hand over to Shashmita now, and she'll talk a bit more about the exciting upcoming projects that UKSEDS are working on.
Thank you, Holly. So yeah, the National Student Space Conference, our big annual event of the year, is taking place in the University of Manchester on the 4th and 5th of March. This is the premier event for students interested in space, putting them all under one roof and uniting them with academics and professionals from across the country. It gives them a great opportunity to network, learn, discuss with over 20 speakers and over 40 exhibitors through talks, a career fair, workshops, and skills sessions. And until the end of this month, the 2-day tickets are only £22 for UKSEDS members, and you guys have been given the instructions on how to join for that. It's quite easy. And also on top of that, right now we're doing a limited 10% discount on tickets, so from now till Monday, and the 2-day tickets will be £19.80. It's a first come first served basis, and use the code there about excited about NSSC 2023 to get those. So yeah. Next slide, please. Another exciting project that is currently being worked on by the membership team is the UKSEDS Space Agents Programme. It's there to create an opportunity for students to build a professional network with people within the industry. There will be opportunities for alumni as well of UKSEDS to share their experiences and advice for getting into and working within the space sector. The programme will allow students to get a better insight into the space sector, as well as develop skills that are key and beneficial for a career in the space sector, whether in the academic setting or the corporate world and everything else in between. So more details are to come soon for that. And there's so many more things going on in UKSEDS. It's a constantly evolving and developing organisation. So we have an active social media platform. We've got a UKSEDS podcast. So yeah, please get involved if you can. Thank you so much for listening. If anyone has any questions, please let us know.
In the meantime, I'd just like to say that at the end, we'll be having the Space Careers team coming in to discuss their sector and how we can basically benefit from what Space Careers does, which includes doing third-year projects and stuff along that area with other industries, but stick around for that. So now Lee will do his presentation.
So hopefully this will work. So can you see my presentation at the moment?
Yep.
You can. And if I go to full screen. Now, do you see the full presentation?
Joshua Finn is a graduate engineer at TALES UK's Leadership Development Programme, where you're working on the Lightspeed satellite constellation. In his spare time, he runs Astroverse, which advertises over 40 space lectures, conferences and events in the UK every month for free. He's also a STEM UK volunteer, an EDT Industrial Cadet Project mentor, and he's participated in the 2022 Space Generation Congress work group to identify skills gaps in the UK space industry. And he is going to give us a talk about why you should consider graduate development programs.
All right. Hello. Yeah, so that's a pretty old picture of me. I need to get that updated. I've not had a photo taken of me for a while. So I'll just get my screen shared up now. So can you see that?
Yeah.
Perfect. Okay. So first of all, hi everyone. I'm Josh, as mentioned, and I'm with the TALES UK Leadership Development Programme. This is TALES UK, not TALES Alenia Space. I'll make that distinction now, but I also want to go through the importance of actually why diversity in your career is important, especially at this early stage where we have opportunities ahead of us. So we are going to get straight into it. And yeah, that's a picture of me with a broken arm holding a baby. And now that's let's add some context to that. So this was just after I'd graduated from University of Leicester, and I went out and I celebrated by losing an arm wrestle, and I really, really lost. So I I'm thinking at this moment in time with that's my niece actually in my arms, and I'm very passionate about space, and I want to think, how do I get other people interested in what I'm interested in? Because in my brain, I think I'm interested in something, I love something, other people should love what I love. That's a very bizarre way of thinking, and I think we're all space nerds from birth, right? Aren't we? We were always wanting to be an astronaut. And I actually, this was probably at this moment I was thinking to myself, I didn't always want to be a space nerd. I wasn't always interested in space. To tell the truth, when I was a kid, I wanted to be an artist. I was interested in drawing, and then eventually I wanted to be an architect. So how did I go from wanting to do art at university to ending up working at a technology company and wanting to work in space? So it kind of started with this guy, this tattooed specimen here. If you might know him already. This is Matt Taylor from the Rosetta mission, and he is fantastic to meet. And I got to listen to him present at the University of Nottingham, and it showed me almost how diverse the space industry is, and showed me all the roles that are important within space. It's not just for people who have physics. It's not just for people who have engineering. We are a much more inclusive group than we necessarily let on at first. So at this point, I decided I want to be in this industry. This is a cool industry. And then I began to find that I could actually apply some of my ideas around arts and creativity, or supposed creativity, towards engineering. So I did in my A-levels, I did design technology. That was my favorite topic. I got to design and build something, and I like being able to be hands-on with my work, and I still like to do that to this day. I went to the University of Surrey, and when I put whoops around that, it's not at all with the University of Surrey. I loved the university itself, is fantastic, but I made some, there was a change of plan. I was originally going to be there for 5 years. I was going to be doing an integrated master's in a year in industry. That didn't happen. I did 3 years instead. What happened, unfortunately, was in my second year, we're all going to find that our plans are going to have to deviate. And I didn't perform as well as I needed to in my second year to be able to continue my master's. This was a very difficult time for me because I was thinking, okay, what am I going to do? I'm not going to have a master's degree. And it felt that was something that was going to make me stand out. And not only that, I wasn't going to have a year in industry. And we know the iterative cycle that companies are always asking for us is that we've got to have experience. Well, to get in order to get the job, well, to have the job, we need to have experience, and it carries on. And it's a cycle of it's a cycle I'm sure that a lot of you relate to. So this was also at the very end of my degree. COVID happened basically, and people, if it was hard enough to get a job beforehand without any experience, it was even harder afterwards. So I went to the University of Leicester to do my master's, and I did a master's in space exploration systems. And space exploration systems, it was honestly one of the best years of education I ever got. Even though it was mostly in lockdown, I loved the topics, and I can't recommend sort of working around the university as much as I can. And then, as well as this, this was my first interaction with the UKSEDS, as I got to join a rover team, and I was the project manager for that team. As everybody else was a first year, I was a postgrad. That was more or less how it filled in. And then at Leicester, I applied for Thales, and I specifically applied for their graduate rotation program. Now, a disclaimer as well, I'm not here to specifically advertise Thales. I'm here to talk about graduate schemes in general. I'm specifically going to focus on graduate schemes with big companies, and they're unique. So the vast majority of the UK space industry is small to medium enterprises, and that means companies under 250 people, and also turning over 50 million, less than 50 million in profit each year. These companies, as you can probably tell from listing, they're a bit bigger than that. And so there's a good variety across the board of what they're offering. And there's a big variety across the actual grad schemes they offer themselves. So a lot of these are 2-year programs, some of them are 3-year programs, some of them are 4. Thales is a 4-year graduate program. Some will send you back to university. Why do you want to go back to university? Actually, it turns out can be quite useful to be returning. So why specifically with big companies should you be considering a graduate scheme? And it comes across fundamentally in diversity. Can you still see the screen, by the way? Is it all going okay? I'll take silence as yes, you can still see.
Great, yeah.
Perfect, just checking. So diversity is key. And simply because a company that is a large company, a larger company such as Thales, such as Airbus, they have more resources, they're going to be able to do more. There's diversity of people. This means there's going to be a more diverse network that you're going to be able to connect with. These aren't going to just be people in one location. There can be multiple locations across the country, and not just across the country, but countries. You're going to be able to meet other people from abroad, potentially, and that will have a massive impact on your career. Also, diversity of industry. All of those companies, they're not focused specifically on space. And you may think, well, we're all space nerds here, aren't we? We're all doing astrophysics. Why do we care about cars? Why do we care about planes? I do like planes, to be fair, as well. But there is a reason that Formula One companies hire aerospace engineers, because a lot of the experience that aerodynamicists have is critical to making your car go fast. So there is a lot of crossover between these industries, and that's how they all become one company. Another one, as I think I've highlighted a bit earlier on, was diversity of location. There is more opportunities to travel between different locations. You'll be able to visit more places. You'll have more experiences. And you'll actually, what I found is early on in joining Thales, one of the most important things was my experience of going to different sites. I'll come on to that a bit later on. And then also diversity of support. Bigger companies have more resources, and joining a graduate scheme, you are going to be invested in, and they're going to invest a lot of money into you because you're extremely valuable. And also to a lot of these other groups that they're training you potentially to be taking up greater roles in the future, and they want you to get as much experience as you can as early as possible across a broad range of different disciplines. So, for example, within the first 3 months of me joining Thales, I was offered the opportunity to go to France for a conference, a Thales internal conference on scaling up agile frameworks, which again wasn't necessarily something I had experience in, but I was interested in it. I expressed interest. I told my manager that this was something I was interested in, and they sorted it, and I got to go. So that is something that an SME isn't going to be as easily accepting of. It's much harder to get that form across. So there is more or less more diversity and opportunity for you in joining a big company at this early stage in our careers, because at this point we don't have as many commitments. I mean, I'm 23 at the moment. Again, that wasn't my kid. Whilst we don't have as many commitments in our life, we have more opportunity potentially to be able to do certain things, to be able to move around. And that's something that I've tried to do myself. I guess that could be, there we go. Yeah, sorry. So my first role was in test equipment. So not exactly space. And I remember having a call with my manager, and they told me I was going to be in the MEMS department. I then quickly searched up what MEMS stood for, MEMS. So microelectrical mechanical systems. I was thinking, oh, so I'm going to be working microelectrical mechanical systems. And they said, no, that's just an acronym. It's the wrong acronym. You're going to be working in the measurement equipment managed service. So I thought I was going to be looking after people's steel rulers. I was thinking, well, what am I going to be doing? I've been trained to be an aerospace engineer, and I've been doing systems, and I'm going to be basically looking after people's stationery. And couldn't be further from the truth. And as someone who is still dedicated to going into the space industry, not being in the space industry for my first year was great. And it was a great opportunity, and I wouldn't want to replace that year with a year in the space industry. I got to travel to multiple different locations, and that's actually very important to see in a big company, because you get to see how different sites work and all the different amazing people and all the amazing projects that they're doing. You see more, you get to experience more. And at this point, I got to learn more about communication, and as well as communication, how communication breaks down between groups. One of the first projects I had to do was try and get these 4 different sites here, Glasgow, Belfast, Templecombe and Crawley, to all agree on a single way of working in the handling of their test equipment. They all had their own ways of working. They didn't want to do any other way of working. I had to get them to all agree. I was not very popular at first. So that kind of experience is going to be critical in more or less, even at this point, you may even find something that makes you decide you don't want to do space. You've found something you're more interested in. But at this point, having a diverse foundation for your career is important for potentially developing and going down into the space route. So on the next slide, a couple things that I have learned in my very brief career. Being your own salesperson. When you first join a company, very few people are going to be able to speak for you because they're not going to know you. The person who's going to know you is you. And I messed this up completely, it turns out, in my first year. My boss had no idea, she told me, about some of the other projects that I was working on outside of work, which included Astroverse, which was a monthly mailing list, which was mentioned, as well as numerous other projects and volunteering opportunities, which I get to do and I enjoy doing. And she only found out because someone else told her. And that was after a year. So she thought all I was doing was just my job and then going home. Your bosses are very interested in what you do. They're interested in seeing you grow and seeing you develop. A good boss will want to support you. Eventually, what will happen is other people will become your salespeople. There was a really good TED talk actually by I should remember their name, but it was about the idea of a sponsor, someone who will speak for you in the room where decisions are made about you when you can't speak for yourself. And that is important. And it starts with you selling yourself and finding those people who believe in you. That doesn't mean you can't just not do any work. It's not just about speaking for yourself. You've got to deliver the goods. And that's another thing as well on that, is pacing yourself. No career is going to look the same. I've seen people who are advertised on the Thales homepage at the moment of all the amazing things they're doing. They've got interviews, and it's completely different to the career that I'm doing. And then you get to see all these fantastic things and you wonder, should I be at this point where I'm doing lots of interviews with lots and lots of amazing groups? And there's one person who who I know of on my program in the same year as me. He hasn't been doing lots of these interviews. What he has been doing is he's learned 3 different coding languages and is being asked by multiple different companies at the moment to be doing work for them. So he's getting an amazing experience, and it's a completely different career to someone else. Again, this comes back to the point of diversity of your opportunity. And I'll come to imposter syndrome and this really, really terrible plug. But also knowing where you fit. Your boss thinks you're useful. They wouldn't have you if they didn't think you'd be useful. So understanding where you fit, and the best way to do that is ask. Ask how I can help. Just go to your boss, say, I've not got as much work at the moment. I feel I could take something else on. How can I help you? And your boss will want that. They want proactivity in how you work. That doesn't mean working longer hours than you're contracted to. But if you have spare time, you can always ask, and your boss will be very happy to give you extra work, I promise. Another one is be social with your colleagues. People who you meet now and in great communities like UKSEDS, they're going to be around in your life for a long time. I'm still in touch, fortunately, with only a couple people from my university, and I regret that. I wish I was in touch with a lot more people. I have 1 or 2 close friends who I'm still in touch with, and they're still in this same industry as me. And when I say be social with your colleagues, I don't mean necessarily going out always and having a drink. Control how you want to be social. Do things that you want to enjoy. You can suggest things. One of the first experiences when I was on my when I was at Thales was going to the pub. Now, I don't drink for numerous reasons, and it's something that I felt was going to kind of divide me from other people who wanted to be social. And the first couple of times we were going to a pub, and everybody was getting slightly tipsy, and you feel sometimes that this isn't something you're as interested in. So how do you change that? Well, you suggest things that you want to do. I really like going for walks, and I suggested that we in a group go to a park and go for a walk. And other people who love going for walks joined me. And so you were able to be social with your colleagues in a different environment. And generally, as a rule, things you like, there are going to be lots and lots of other people who like them as well. So don't be afraid to ask and suggest things. So that's a key important thing. If you don't want to, you don't have to just be drinking to be social. You can do other things, and that doesn't change when you join the work environment as well. And the other one is attend conferences and networking events. Meet other people outside of the company sphere. I've shamelessly plugged Astroverse there again. But it's an important moment to be able to get a broad community and a broad network for yourself, because you'll find opportunities aren't just within your company, but also outside the company as well. And the final one is on imposter syndrome. And I've experienced imposter syndrome, and I experience it to this day. I was talking to a friend in a canteen, and I was saying, do you sometimes just feel you shouldn't be here? And she told me, yes, every other week. We all experience it. We will. And it was only recently that I heard someone actually articulate it correctly almost. It's that when we're dealing with something new, who's to tell you that you're unqualified to solve a problem? A lot of these problems that we're going to be facing in our careers, again, no one's walked the career that you've walked. No one's going to have made the decisions that you've made exactly. So who's going to be able to come to you and say that you're unqualified to solve a problem? The reality is the only person is you. But are you really unqualified to solve that problem? It's all really going to be in the choice that you can say. And it's, bluntly as it is, it's fake it till you make it. I wasn't able to do any coding when I went to university at first, and then I learned how to do MATLAB. I couldn't do MATLAB for the coursework assignment. I still passed the coursework assignment, and I brushed off my MATLAB. It's a case of, yeah, as bluntly as it is, faking it till you make it, and you will make it, and then it'll actually be substantial, and then people will say you are qualified, because actually you are, and it started with you. So now I do space stuff, which is the cool stuff. It's not just test equipment now. I get to work on the Telesat constellation, which is over 300 satellites and 4 modules. And what I get to do at the moment is some hands-on testing for some prototype components, which is really, really cool. Thales, this will be a brief bit on Thales, and I can talk now a bit about what Thales does and why I would recommend going for Thales as a graduate program. So you will have the opportunity to do space stuff eventually if you go for it. Now, Thales Alenia Space has identified that graduate placements are important, and the number of them are growing. And it's also, Thales Alenia Space in the UK is growing itself. The number of sites is going to increase. There's currently Harwell and Bristol, but there are 2 more sites which are in development. And in 2020, no grads on my program were doing anything space related. And then in 2021, 2 people got in touch with Thales Alenia Space and said, we want to work for you. Can you give us an offer? And then 2 people suddenly started working for them. Thales Alenia Space then said, oh, these guys are really good. They do a lot of work. We want more of them. So they increased it to 5. And it's likely next year to double as well. So a lot of people join this program to take part in space, and a lot of people like me are massive space nerds and really want a space placement. That's part, again, on your branding side of things, of selling yourself. You've got to sell yourself as you're really interested in space, because there's going to be a lot of people wanting those placements as well. So if you also want to go for those space placements, which you can get, you're going to have to compete for them. So it's a challenge there. But along with that comes a lot of great opportunities to work in a very broad environment, and you can apply that later on when you might decide you want to move on to another company after 4 years at Thales or 2 years at Airbus, and then you might want to work for an SME, a more innovative, a company which drives further down the specific route of innovation. So that leads me on, I think, to everything that I've covered. In summary, these kind of programs are a very good opportunity for diversity in your career and creating a plethora of opportunities for yourself. If you either want, that means if you don't know exactly what you want to work on, it's a great opportunity. Even if you know exactly what you want to work on, it's still a great opportunity. So I'd recommend applying for as many of them as you can, and hopefully you get involved in them. Thank you very much for your time. I think I might have overrun. Any questions? Ooh. Cool, I think all good.
If there are any questions that do come up, I'll make sure to send it to you via email.
Cool. Yeah, sorry. Oh, well, thank you very much.
Thank you very much.
Okay, now we've got a couple of talks from a few of the branches, UKSEDS branches. So now starting off with the Portsmouth University Space Society, we'll talk a bit more about their society and the projects they're getting with. Hand over to you.
Hi there. I hope everyone's having a great UKSEDS event. And basically I'm here to sort of represent the University of Portsmouth and the brand new Space Society, which started up over the summer of 2022. So if I just share my screen very quickly, entire screen. Okay, so can everyone see that?
Yeah.
Awesome. Okay, so at the University of Portsmouth, we started up a brand new Space Society. We started up over the summer of 2022 because basically, as we come on to, I am a course representative. So I was in my first year at university and we were listening to sort of feedback from students. So as a course representative, basically my job is to connect students with their lecturers and also boost engagement with the course. We were finding that sometimes, especially on the astrophysics courses, people were feeling like there was no interplay between the different years, and sort of like they would feel like they were just doing their course and just doing the course, there wasn't anything sort of space related. So we listened to that feedback and we looked around and we saw what we could do. We basically contacted the Students' Union at the University of Portsmouth and we started up the Space Society. So I am the president of the Space Society. I'm the one that started it up. I'm currently in my second year of astrophysics and I am loving it. The University of Portsmouth has been a great thing for me. When I first joined my first year, I was pretty much an introvert. I was very introvert. I wasn't very social, but joining the University of Portsmouth has really sort of boosted my confidence and has really sort of developed also my technical skills as well. And yeah, so I'm also an outreach demonstrator for the Institute of Cosmology and Gravitation, which I will get onto, which is basically the research centre at the University of Portsmouth. So at the University of Portsmouth, we have physics and astrophysics courses. We do them BSc and also MPhys, which is sort of the master's program. I'm personally on the Masters of Physics, Astrophysics and Cosmology, and I'm loving it so far. We have developed technical skills, we've done computing, we have done mathematical physics. It's just been a good overall experience. We also have the Institute of Cosmology and Gravitation, which is the research centre at the University of Portsmouth. So they specialise in theoretical and observational cosmology alongside gravitational waves. They were the pioneers in gravitational waves back in when they first got detected at LIGO. Some of our team worked on basically the detection and the processing of the signal. And speaking to them, I really look up to them. So who are we? We are the Space Society. Our main aim is to bring together people of all backgrounds and inspire them to consider a career in the space industry. We have over 100 active members, which, considering the fact that we haven't even been around for a year, I think is really successful. We've had really positive feedback. And basically our aim is we have people from English literature, we have people from law courses. It's not just focused just on the astrophysics and physics courses. We also have people from computing. So basically we have a multidisciplinary team in which we can then form competitions. We can, collaborate with other universities. We can open up placement opportunities. We've actually landed 3 students with placements at various companies, year-long industrial placements. We're completely student-run. We have 6 members of the committee, myself included, and yeah, it's just been a great experience all around. We are supported by the University of Portsmouth and also the Institute of Cosmology and Gravitation, which has been great, which means we've been able to put on pub quizzes, we've been able to put on tours around. Actually, on the 8th, we are touring a local company to us, and we are basically opening these opportunities to people who might not necessarily have had them before. So here's a little bit about the committee. Myself, Lauren Young, I am the president. Basically, I'm pretty much the overseer of the society, so ensuring that it runs all smoothly. If anything goes wrong, it's unfortunately on my shoulders. We have Kai Wilson, who is our vice president, who just sort of supports us in the smooth running of things. We have Ria, who is our secretary, so she deals with all the risk assessments and things like that. And we have Beatrice, who is our treasurer, so for events, sometimes they are paid, sometimes not. So she deals with all the finances. We have Chilla, who is our event secretary. So we have weekly events, which basically she is the overseer of that. She brings forward her sort of ideas on what we can run and what sort of engage students with the courses. And we also have Thierry Fox, who is our social media manager. So if you contact us on one of our social media, you'll be talking to him. So our future plans. So we are actually looking to purchase a telescope. We're currently raising funds so we can put on stargazing nights. And as you can see on the right hand of the screen, Thierry, our social media manager, is very experienced with astrophotography. And we're hoping to run astrophotography classes, but we're sort of looking at getting a bit more resources for that. We're also reaching out to companies outside of Portsmouth. So we're actually contacting companies in Stevenage to sort of have tours, have talks, open these opportunities. We're also starting this Portsmouth Space podcast. Now, this is very early stages, but it's something that I'm really passionate about. Basically, we have people from all different courses across the University of Portsmouth come and sort of share their passion for space, share why they want to get into space, and also talk about different topics. So for 1 week, for example, we talk about gravitational waves. The other week we talk about black holes, just sort of like try and get the University of Portsmouth engaged with the space industry. And one of our strategies to that has been joining UKSEDS, which has been brilliant so far because, we are brand new. So we're trying to get our name out there, sort of give everyone connected. We also are looking to run competitions between universities and other societies. So if you are a member of a society and you would like to sort of collaborate with us, feel free to contact us. I think I got an email at the end of the presentation. Excuse me. We are also promoting placement and graduate opportunities. So like I said, we have landed people on placement opportunities for year long. So if that seems good, feel free to contact us at space@upsu.net. My name's Lauren Young, and that is my email at the bottom. That is my university email, which is up2060473. Feel free to contact us on any of our social media and just sort of contact us. That's pretty much everything I have. Does anyone have any questions?
Doesn't seem that there are any questions at the moment, but if there are any questions that do come up over the course of the next few days, I'll make sure to email them over to you. But thank you very much, Lauren, for your presentation.
Thank you.
It seems like you guys are going to go to great heights. So
yeah,
well done.
We're really hoping to sort of get our foot in the door and sort of like see people from who are in year one at the moment and just sort of like progress them on, see how they sort of connect and things like that.
Thank you very much.
Thank you.
Thank you. So next coming up is our another branch who will be presenting KCL Space. So I will pass that on to you.
Do you want me to share my screen?
Yep.
Okay. Okay. So. Okay, can everyone see the front page?
Yeah.
Okay, perfect. Okay, so we'll start. So hey guys, hey everyone. We're KCL Space. If you haven't heard of us already, then I would say shame on you, but I feel that's a bit harsh. But yeah, we're KCL Space. My name is Isha. I'm currently the president of KCL Space, and we've been running since 2017, and we are just trying to engage more people in the space industry and to increase our awareness within our university as well, as King's College London doesn't really have a big space section, so we're just trying to increase that, and that was part of our aims. So yeah, a bit more about who we are. We were founded in 2017, as I said, under the Department of Physics as a gold society from KCLSU. What we do is we provide academic, sport, mentoring sessions and networking events alongside social activities such as winter balls and parties and stuff to engage our members and get them to have the full university experience. And the picture on the left, as you can see, is our team last year at the award ceremony. So that's when we won the KCLSU Arnhem got the Lifetime Membership Award, and our Vice President got the Laurels Award, and we won the KCLSU Activity Group of the Year Award at the ceremony, which is the best award an activity group can win at King's, which we're really, really grateful for. And yeah, so our aims. Appian, do you want to go over our aims?
Yeah, hi everyone. Our aims is basically to bridge the gap between the niche of the space industry and the students. So provide our students with opportunities to develop skills and build a network in the space sector. And we also want to increase the accessibility of our activities and everything for everyone to enjoy space at King College.
Mm-hmm. So quickly about membership benefits, something similar to our aims, but we have a lot of access to opportunities. So we've partnered with companies such as UKSEDS, IP, the RAS, ISEC, and we're working to partner with more companies as well to give more opportunities to our members. We also have a big community, so roughly around 300 members now, and we try to encourage university students from a wide range of academics, not just STEM students, but also students within space medicine and space law. We're also building skills as well. So we have a rocketry team, so they can build rockets. And we also have upskilling sessions. We get to learn more about coding, about team leadership, and just general skills that you would need in the space industry. And it's obviously free of cost. So KCL Space, we pride ourselves to being a free society, and because we want to encourage everyone to join our society, and because space is for everybody, and we feel like because space is universal, our society should be as well. So yeah, KCL Space is for everyone. A bit about our demographics. So we have a good range from female to males and others, about 56.6% males and 42.3% females. But we are trying to increase that to make it a bit more even. And most of our members, our members are around 300 this year, which is about treble since last year, which is really, really good. It shows that there's a lot of interest within the space industry and what we're doing, and we only hope that it grows in the coming years. So in our part of our departments and branches within KCL Space, so one of our branches is KCL Rocketry. So the KCL Rocketry team is the KSRT, and it was established formally this year. And all the pictures you see here from the stuff that we've been doing this year. And we've applied for UKSEDS NRC competition. And if you see those two rockets, those are two rockets that were made during 2020, but they weren't able to be launched because of the pandemic. And some of our aims are to try and launch those two rockets and also make and launch our own rocket for the NRC competition. And our team are very excited. They're very passionate. They really want to achieve well. And although not a lot of them have experience with rocketry design and body design and all that kind of stuff before, they all seem very eager to learn. I've been hosting workshop sessions for them to try and teach them and guide them. And it's looking very exciting so far. We also have a space medicine, a branch within our society. And space medicine works to increase the awareness of space medicine as a topic within the space industry, as it's a growing field and not a lot of people are aware of space medicine. And because King's College London does have quite a big students who are medics or going into medicine at our Guy's campus. So we partnered with societies such as KCL ASMS, which is Aviation, Medicine and Space and Aerospace Society, and also Synthetic Biology Society, which are both based at Guy's campus. And together we've had a few events, including games nights and lecture talks, and we're hoping to have some more in this semester as well, and to increase awareness about roles in the space medicine sector, and to get people excited about the space sector, especially within space medicine. We also have a space law as a branch, and this branch aims to do the same thing as space medicine, but in space law. So space law is also quite prevalent in the space industry at the moment, like who owns space, who can own land on the moon. All these kind of things are very important, and we have a lot of lawyers in our Strand campus who are very interested in space law. So our space law division works to increase knowledge of the space law industry, and also to, as you see from the pictures, they have host moots. So the last moot, this was from the pictures from the British Interplanetary Society, where they did a moot, and they'll also be hoping to do one in Spain this semester. I think the finals are happening in Spain, so we're still working on that, and hopefully we'll be able to encourage our members to join and learn more about space law. So it's quite exciting. We also have podcasts. So Appeline can talk more about the podcasts.
Yeah, we also have a podcast series that's called Across the Corman Line. So this is a series where we interview people from the space industry to educate our members about the space sector in general, or also about more specific space-related scientific phenomena. This is a great opportunity for members to learn more, but also for people to join the subcommittee, which is very important for subcommittee members to be able to make a network and to connect with people from the industry. So these podcasts are available on Spotify, Anchor, and YouTube. And yeah, it's a great opportunity for our members, but especially for the subcommittee members.
Yeah, and you can also listen to our podcast on Spotify, Anchor, and YouTube. So feel free to check those out. Yeah, so part of our events. So previous events that we've had so far within KCL Space include, but not limited to, our Project Alpha Centauri Hackathon, which is the picture at the top. We've had talks from companies such as AMC, which is on the left, and rocketry sessions. And also we had social events such as our Winter Ball. And we also hosted the National Student Space Conference last year with UKSEDS at our Waterloo campus, and you can see some pictures of that at the bottom. And we also worked alongside ISET in the summer to host the Mission Discovery Program at our Guy's campus, where KCL Space members volunteered to mentor the students as part of the program, and we met some astronauts, and it was a great time. And future events, as in events we've done this last semester, so semester one. So we had our welcome event where we had some games nights. We gave the same presentation, something similar to our members to introduce them, especially to the freshers. We had some pizza, we played some games, did a Kahoot as well on space law and gave out prizes. We also had some games night as well, where every Sunday we have like a kind of refreshing kind of hour. We just chill and relax every 6 p.m. on Discord. So quite a lot of people do get stressed throughout the week at university. So we created this safe space where people can just join online and play some games, get to know one another. And if you're not comfortable with showing your face, you're completely online, so you can be anonymous. But it's a way to just rewind after the week. And Among Us happened to be a very popular game on the Discord chat, and now some people started calling it the Among Us Society. So that's great. And we partnered up with KCL Gaming Society to make that possible. So if you are interested, you can always join us on our KCL Space Discord, 6 p.m. every Sunday for some Among Us and some more games. We also had World Space Week that Apping can go over.
Yeah, in October, we hosted the World Space Week, where we basically organized movie night at King's, where we watched space-themed movies with our members. And we also hosted a sustainability in space talk to raise awareness about the need of a sustainable space sector. So this week, we had a great engagement for our members, and yeah, it was fun and learning at the same time, which was great.
Yeah. We also had our Halloween party as well.
Yeah, we hosted basically a Halloween party at King's, and we had different activities from bingo, face painting, or karaoke. It was space themed, but it was also a way for members to connect outside of classes and to talk, make friendship. We also have a lot of more social events for them to connect that are not related to any science or learning aspect. So this is also very important for us.
And yes, we had our space law meet, like I mentioned, at the British Interplanetary Society. And hopefully our space law team, as you can see here, will hopefully be representing us in Spain later on in the semester if things go well. We also have stargazing. So last semester, we introduced our stargazing sessions. And to be honest, we didn't think it'd be that popular, but actually was extremely popular. And we completely sold out our 50 free tickets for the event within a couple of hours. And we've had a couple of sessions since then. We had the telescopes to be able to see a deep space telescope, which could see the Andromeda Galaxy. And we also had another telescope that you could see the moon, Mars, and Jupiter, and some of the planets as well. And people could take pictures from that telescope as well. So it was a really fun event. Lots of people enjoyed it, even though it was really, really cold, because we did do it during November. And it was very dark and cold, but people did enjoy themselves, and we're hoping to host some more sessions in the future. Of course, being a London society, it's quite difficult to find places within London that are free from clouds and are relatively easy to travel to. But we managed with this location, which is Primrose Hill. It was relatively dark and not that much light pollution in the area. And it was not too far away from our campus, which means more people could make it there. Weather will always be an issue though, so we'll try to host some more stargazing events, but of course it's all weather dependent. So we'll see. We also hosted, we were one of the societies who helped host the KCL Tech Summit, which happened in October last year, held in Bush House at King's. There was a summit with lots of companies, technical-based companies who came along with the KCL Tech Society. KCL Space had our stand. We broadcasted our society to the attendees who joined, gave out opportunities, and a lot of people joined the associate membership that we have, because to be a KCL Space member, you do not need to be studying at KCL. And we showed our rockets, and I was also on the panel session for leadership, and we had a great time. And a lot of our members who wanted to join the event could also join as a volunteer, which meant that they could become either a general volunteer or a media volunteer. And the media volunteers were taking lots of pictures throughout the event, and they got their hours of volunteering in through KCLSU, and they also uploaded some fantastic photos of the event, which is why we have so many. So yeah, we could talk about the winter balls, like highlight social event of the year.
Yeah, in December, we hosted the annual KCL Space Winter Ball, and this year's theme was a masquerade ball. So this is like a very popular event amongst our members, and because it's basically a great way to socialize after the end of the first semester. And we also tried to keep the ticket prices affordable for members to attend, and everybody really enjoyed it. It was, I think, one of the most popular events of the year. And I think this was our second annual Winter Bowl, and we aim to do it every year since
Yeah, so last year was the first time we hosted it, and this year was the second time, and it was very, very popular. We completely sold out all our tickets, which is great. Yeah, so quickly about our upcoming events. So hopefully we're going to be hosting our X3 Space Conference this semester in March, as along with our second time that we're hosting our hackathon, which is PackHack Volume 2. And these events will, our X3 Space Conference was an idea that was made from hosting NSSE last year. And we were so inspired by hosting it with UKSEDS that we wanted to host our own space conference. We'll also be trying to host our outreach event as well this semester as well, trying to get some students to come along and to get inspired about the space industry, and hopefully be doing some lab tours as well. Also, to explore our universe with us, you can also join us on Instagram. We have quite a big social media following account on our Instagram, Facebook, LinkedIn, YouTube, and Twitter. But our Instagram is most popular as students tend to use Instagram a lot. And yeah, so follow us for more posts on space and space news, and to be updated on all of our events. And yeah, so just some pictures about our committee. We have quite a big committee. I have to manage quite a lot of people, but it's all good. And we have, like I mentioned, we have the space law and space medicine branches, rocketry, and we also have Cameron, who's our wellbeing lead as well. And we'll be hosting a bake sale on Monday as well for wellbeing. And yeah, we have quite a big vibrant committee, and people can always join as well. So we try to make sure we recruit people within first year for our subcommittee, so that our committee has a complete range of people representing the whole cohort within the university. So yeah, to join us, like I said, you do not need to be studying at King's to be a KCL Space member. You can get the associate membership, and we've got a QR code over here, so you can scan that to access more information and to follow us on our social media channels. And if you need to email us for any opportunities or questions or inquiries, you can contact us on contact@kclspace.com. And I'll finish off with a quote, which is, "Space is for everybody. It's not just for a few people in science or math or for a select group of astronauts." And that's our new frontier out there. And it's everybody's business to know about space, which I completely agree. Space is for everybody, and it's not just STEM students who can join the space industry. And hopefully with this next decade or so, the UK Space Agency will grow, and with it, the students can also find more opportunities to join. And that's part of our aims at KCL Space. So yeah, thank you for listening. Does anyone have any questions?
Thank you very much, Isha. It doesn't seem like we have any questions at the moment, but thank you for your presentation. We are going to now move on to a presentation by Jacob from Space Careers. So, Jacob, if you'd like to share your screen.
Hello everyone, 1 minute, let me just share my screen. Is that working?
Yes, it is.
Brilliant. Thank you very much for having me. It's a pleasure to be here. Lovely to hear those few presentations earlier. So yeah, my name's Jacob Smith. I'm here representing spacecareers.uk, which was set up by UKSEDS back in 2015 and has basically operated as the careers arm of UKSEDS. So we're student-run team, and we are here basically for anyone interested in the space sector to come and find out about opportunities in their career, find out advice on how they can get those opportunities. We also have a jobs board where you can find different opportunities. I'll explain a bit more about that later. And this is only a 10-minute presentation. It's kind of an abridged version of a longer presentation. So if you're interested in us doing a longer presentation for your society, then don't hesitate to reach out and we can arrange that. But hopefully this is a quick overview. So I just start by a little introduction to the UK space sector. So over 1,000 space organisations in the UK, comprising nearly 50,000 people. And you can see over the past 5, 6, no, it's 2023 now, sorry, 8 years, the space sector has grown so much. massive growth, and that has led to the creation of the National Space Strategy, the first one in the UK in 2021. And the UK government is really serious about space. And what does that mean for you? It means lots of new opportunities, lots of investment, and really need to invest in education and opportunities for younger people. And that's exactly where we come in as well, in raising awareness and supporting you with these opportunities. So similar to the quote that we just ended on, I'm going to kind of touch upon that as well. I completely agree that space is for everyone. That is what we're all about. Space, there are no rigid routes into the space sector. So on our website, for example, we have some interviews with professionals working in the space sector in a host of different jobs, and you can see that everyone on that interview page is taking a different route into the space sector. So don't think that you have to follow a certain path. There are obviously some kind of set routes, but they're not fixed. I'm going to talk about a few different jobs. There's not enough time to talk about everything. So obviously there's plenty more jobs out there than I can cover now. Don't think you have to stick to what you want to do right now. You can change your mind, and that's no problem. I've actually cut out the slides about my career path, but I've changed my mind and work in a completely different area now to what I got my education in. And yeah, just do what you enjoy, and you'll find your way. I think that's the key thing, really. Don't do something because you think you have to do it. And just to talk about a few of the different jobs. As you can see, there's a variety: STEM, non-STEM. I thought just before I came on, I could maybe take the example of the recent space launch that was in the UK, because I was looking at policy and law, and that just made me think of all the regulations that have had to be made to create this new ability to launch rockets from the UK. And you've seen a lot of the media around that, a lot of communication to the public about that. So obviously, communicating comes into it. Or the technology that was actually involved, building, launching the satellite and the rocket itself, creating lots of jobs, and the satellite itself is obviously helping people in the local area. There are some satellites to track illegal fishing, for example. Or do some Earth observation, helping farmers, and these can really help public. What else have we got in here? Improving the lives of people. Yep. So as I said as well, like tackling big problems as well. For example, the climate crisis, space can really help with that. On top of what you might think of normally, and when you think of space immediately in terms of exploring the universe, trying to understand physics on the grand scale in the universe, and teaching. No one can do any of this without educating people on how to do it. So there's a huge variety, as has been touched on already. And I'm not entirely sure on exactly what stage everyone is at, but there's a variety of different routes and options, no matter what stage you're at, really. Lots of different choices. The space placements in industry program will be coming out soon with opportunities for you to do an internship this summer. So have a look out for that. If you could do an internship this summer, different opportunities, jobs, graduate programs, masters, PhDs, or a break. I'm sure a lot of you are working very hard during your studies, and it's no problem at all to take a break afterwards. A few master's courses that I've taken from our website and put on here. This is actually for an engineering and physics presentation originally, so these are all mostly, I think, related to those subjects. But as you can see, there's a host of different opportunities. If you realise, like I did during your undergraduate studies, that you wanted to specialise more in space afterwards, then these can be a good way of doing that, to get some space-related education. So I won't stay long on here. This is all on the website. PhDs likewise, different places you can find out about PhDs, our website being one of them, and there's some other websites for PhDs more on some specific topics, for example, environmental science or Earth observation. These groups will accommodate PhDs in these areas, so have a look at some of these organizations if you're interested in doing a PhD. Tips for getting a job after university. work experience is key. It doesn't necessarily have to be related to space. At the early stages of careers, I think companies generally just want you to have good work etiquette. So, you know, you can turn up to the job on time, and you can, you know, they can trust you to do your work. And obviously space experience is more, you know, attractive to them if you've already got some experience doing that. So internships, projects are a great way of doing that. Getting involved in your society. If there's not something specific in your society that you're interested in, you can always do a project yourself in your own time. That will really show your dedication to the subject, to learning and developing yourself, and gaining some skills that you think are more specific to what you need to develop. Generally, keeping up to date with space news is fantastic, to show your interest to the people you're interviewing with. Networking, so attending events like this, attending events like the National Student Space Conference in March. Fantastic place to meet new people, to meet people working in the field, start to build your network. I think that's probably the biggest thing you can do. And taking opportunities, anything that comes your way, you might not, you know, realize at the time how it could help, but try and, you know, get as many different experiences as possible. I think that's, yeah, a good thing to do. Obviously not too much that you overwhelm yourself and can't keep up. Some opportunities for you during your studies. What have we got? Summer schools on. I didn't want to list all the summer schools. There's no room. So there's an article on our website about the different summer schools that you could attend. As I just mentioned, NSSC this year in Manchester. SPIN that I mentioned earlier will be coming out soon. They are 8-week placements in space companies over the summer. You've got the UKSEDS competitions. They're in rocketry, satellite design, rovers, and in-orbit servicing and manufacturing. A satellite challenge, I think it's called, which is run by UK Space Agency. It's worth a look at that as well. Spaceprojects.uk, so that is there for if you are doing your final year project at university or your master's project and you want to do that with a space company, then we provide connections with space companies, basically, who propose projects to us, and then we will share those with students to apply to. So take a look at that if you're at that point in your university career. And finally, ESA Academy. They run, well, this is actually where I work currently, so if you also have questions about this, then get in touch with me, no problem. We run some space-related training courses throughout the year in all different topics, STEM and non-STEM, typically 1 week long in Belgium, and they're a really good opportunity to really hear from experts in the field and develop your skills in some topics. And some other organisations you can look out for as well as your societies. They have space-related opportunities or not, and you can develop your skills with them by volunteering with them. So yeah, take a note of those. And yeah, finally, this is our website, if in case you've not seen it. Heads up, we will be launching a new website in a few weeks' time. So our team have been putting in a lot of work over the last year and a bit, and we are looking to expand our service. And there'll be a lot of new features and opportunities on there, including the ability for you to make your own profile, so you can kind of customize your experience on the website and get a lot more out of it. So keep a lookout for that in a few weeks' time, and we hope that that's going to be a lot more helpful for you to find your space career. Yeah, so my contact details, feel free to reach out to our team or myself. And as I said earlier, if you also want us to come and do a longer presentation, we're very happy to try and organize that. And yeah, any questions, feel free to fire them away. Thank you very much.
Thank you, Jacob. I'm just going to see if anybody's got any questions. Seems like nobody's got questions at the moment, but I have put the email for Space Careers in the chat. So if there is any questions, you can shoot it over to that email. We are at the conclusion of the event. And I'd like to thank all of our speakers that spoke today so very much, especially because of the fact that I did contact a lot of them on very short notice, and they all managed to pull through very, very well. So I'd really like to thank them beyond anything. Additionally, just to reiterate, membership for UKSEDS is free, so make sure to go grab that. NSSC is coming up, so if you can get it before then, it'd be amazing. And I'd pass up on to Holly to speak about that a bit more.
Yes, so just a reminder that NSSC this year is going to be at the University of Manchester on the 4th and 5th of March. That's the first weekend of March. We're planning to have loads of amazing speakers, workshops and panels there over the 2 days, and we really recommend you come if you want to network with graduates and students who like-minded interest in space. We'll also be having a careers event there where companies who sponsor the conference will be having stands, so you can go and talk to them as well. 2-day tickets are currently £22, but as mentioned earlier, we are offering a discount until the 6th of February, so Monday, of 10%. And I don't know if you want to put the code on the screen again.
Yeah, I'll do that.
Yeah. So you can grab your tickets now for £19.80. Also, just a reminder again to email us if you've got any questions from today's talks or got any questions about UKSEDS in general. Alan's put the membership team and careers email in the channel, and I'll put the competitions one as well if you're interested in those. Again, then thanks to everyone who attended today and all the speakers, and we hope to see you in the future at more UKSEDS events.
Thank you, everyone. We are going to head off now, and we seem to have finished exactly on time. So thank you very much.
And thank you to Ahlan for hosting this as well. It's been a lovely event.